Hello there, and welcome to Life Beyond Seen, a place where curiosity slows its breathing and science is allowed to speak softly without rushing to impress or overwhelm. This is a space for long thoughts, quiet wonder, and stories that unfold at their own pace, the kind you can listen to while the world outside gradually fades into the background. Tonight, we're beginning a descent, not just into the ocean, but into one of the least understood places on Earth, a place that scientists study with equal parts fascination and unease. If you find this calm, or if the steady rhythm of discovery helps you unwind, a like or a subscription quietly supports this corner of the internet and helps it reach others who might be looking for the same gentle pause. Now settle in, let your shoulders relax and allow the noise of the day to drift away, because far beyond the reach of sunlight, beneath layers of cold and pressure, lies a part of our planet that still refuses to feel familiar. The surface of the ocean gives us a comforting illusion. Waves rise and fall in predictable patterns. Sunlight scatters across blue water. Ships pass through as though the sea were simply a wide open road. Even storms, for all their violence, feel temporary. They rage, they pass, and the ocean appears to return to calm. But this sense of familiarity ends quickly once depth enters the picture. Just beneath the surface, the ocean begins to change its personality. Light fades, colours disappear, sounds behave differently, and with every metre downward, the environment becomes less forgiving, less intuitive, and more alien. Most people know that the ocean is deep, but deep is a word that hides more than it reveals. Deep can mean a few hundred metres, where scuba divers still roam among coral and fish. It can mean a few thousand metres, where submarines glide through darkness and cameras replace windows. Or it can mean something else entirely, a depth so extreme that human intuition simply stops working. This is where trenches live. Vast scars in the seafloor where tectonic plates collide, sink and disappear into the Earth's interior. These places are not just deep. They are vertical worlds, places where the ocean floor suddenly gives up and falls away. The Kermadec Trench is one of these places. It does not announce itself loudly. It does not sit near busy shipping lanes or popular coastlines. It stretches quietly across the South Pacific, far from most human attention, running roughly parallel to New Zealand's northeastern edge. From above, it looks unremarkable, just another line on a bathymetric map, another contour in a sea of contours. But that line marks a drop so extreme that if Mount Everest were placed inside it, the peak would still sit more than a kilometre below the ocean surface. This is not depth as we usually imagine it. This is depth as an absence, a vertical emptiness that swallows distance and light alike. Scientists know its measurements, they know its approximate shape, they know the tectonic plates responsible for its existence. And yet, despite all of that knowledge, the Kermadec Trench remains deeply unsettling to those who study it, not because it hides monsters, or because it defies physics, but because it exists at the very edge of what humans can observe, measure, and survive. It is a place where equipment fails, where data becomes fragile, and where the environment punishes even small mistakes without hesitation. As depth increases, pressure rises at a rate that feels almost unfair. For every 10 metres of water, pressure increases by roughly 1 atmosphere. At the bottom of the Kermadec Trench, the pressure exceeds 1,000 times what the human body experiences at sea level. This is not pressure that squeezes gently or gradually. It is pressure that would crush unprotected human tissue instantly. Pressure that turns air-filled spaces into liabilities and steel into something that must be carefully engineered just to avoid collapse. In this environment, the ocean is no longer a fluid in the way we understand it. It becomes a weight, an unyielding presence pressing from every direction at once. Light does not survive this descent. Sunlight fades completely within the first few hundred metres, leaving behind a darkness that is not dramatic or cinematic, but absolute and persistent. There are no shadows because there is no light to cast them. Cameras rely on artificial illumination, narrow cones of brightness surrounded by infinite black. Beyond those cones, nothing reflects back, nothing offers visual context. It is not emptiness, but it feels like it, because the human brain relies so heavily on sight to define space. Temperature follows a similar trajectory. Near the surface, the ocean absorbs heat from the sun, creating layers of warmth that support familiar marine life. As depth increases, temperature drops until it stabilizes just above freezing. In the trench, this cold is constant. There are no seasons. No warm currents drift through to bring relief. Everything exists in a state of perpetual near freeze, slowed by the lack of energy, shaped by scarcity, and adapted to conditions that never change. This combination of pressure, darkness, and cold creates a boundary that humans have crossed only a handful of times. Unlike space, which has seen dozens of crewed missions, the deepest trenches of the ocean remain largely untouched. The Kermadec Trench in particular has been visited far less frequently than its more famous cousin, the Mariana Trench. That lack of attention does not make it less significant. If anything, it makes it more unsettling, a reminder that large portions of our own planet remain functionally unknown. What makes this even more uncomfortable for scientists is that the trench is not a static feature. It is not a silent hole that simply exists in the background of geological time. The Kermadec Trench sits atop one of the most active subduction zones on Earth. Here, the Pacific Plate is sliding beneath the Indo-Australian Plate, a slow but relentless process that releases enormous amounts of energy. This movement is responsible for frequent earthquakes, volcanic activity, and subtle shifts in the shape of the seafloor itself. The trench is alive in a geological sense, constantly reshaping itself far beyond human observation. Studying such a place requires technology that operates at the limits of engineering. Remotely operated vehicles must withstand crushing pressure for hours at a time. Sensors must function reliably in cold, corrosive salt water. Communication cables must carry signals across kilometers of water without failure. Even then, missions are often brief, cautious, and incomplete. Data arrives in fragments, pieced together from short glimpses rather than continuous observation. There is also a psychological dimension to this unease. Scientists are trained to seek patterns, to build models, to reduce uncertainty. The Kermadec Trench resists all three. It is too deep for continuous monitoring, too remote for regular study, and too hostile for long-term instrumentation. Every expedition feels provisional, a temporary intrusion into an environment that does not accommodate curiosity. This creates a strange imbalance, where knowledge exists alongside large gaps that cannot be easily filled. And yet, despite all of this, life persists. Not in abundance, not in familiar forms, but in ways that quietly challenge assumptions about what living systems require. Microorganisms survive in sediments under unimaginable pressure. Small invertebrates move slowly across the trench floor. Fish adapted to the Hadal zone drift through the darkness, their bodies shaped by necessity rather than elegance. Their existence raises uncomfortable questions about where life can exist and what limits truly mean. This is part of what makes the Kermadec Trench so compelling and so unsettling at the same time. It is not just deep, it is extreme in multiple dimensions at once. It pushes against the edges of biology, geology, and technology simultaneously. It reminds scientists that Earth still contains environments that operate on rules we only partially understand. As this descent continues, the sense of scale begins to shift. The ocean is no longer something above the seafloor. The seafloor becomes a distant concept, far below the reach of normal reference points. Distance stretches vertically instead of horizontally. Time feels different when observation windows are measured in minutes rather than days. And with every meter downward, the surface world becomes less relevant, less connected, and easier to forget. This is where the story truly begins, not with a dramatic discovery or a sudden revelation, but with the slow realization that even on a planet we call home, there are places that remain fundamentally foreign, places that resist familiarity not because they are hidden, but because they exist under conditions that strip away human advantage. As the descent continues, the trench reveals not answers, but deeper layers of uncertainty, and it is within those layers that the quiet unease begins to take hold. From the surface, the ocean presents itself as a plain, not perfectly flat of course, but broad and continuous enough that the mind treats it as one. Horizons stretch cleanly, directions make sense, depth feels optional, something beneath rather than something dominant. This illusion holds remarkably well until maps begin to show what lies below, and even then the symbols fail to communicate the reality. Lines and gradients flatten what is in truth a sudden absence, the place where the ocean floor does not gently slope or gradually deepen, but simply gives way. The Kermadec Trench is one of those places where the familiar geometry of the world breaks down. Instead of a gradual descent, there is a sharp interruption, a long scar etched into the Earth's crust where the seafloor tilts downward and then continues dropping far beyond the depths where most marine life, research vessels, or human imagination ever reaches. This is not a valley in the way land valleys are understood. There are no hillsides that invite slow exploration. There is no bottom that reveals itself willingly. It is closer to a wound stretched across thousands of kilometers, formed not by erosion or time alone, but by force that never stops acting. Geologically, this place exists because the planet is restless. The Earth's outer shell is broken into vast plates that float atop the semi-fluid mantle beneath. These plates move slowly, almost imperceptibly on human timescales, but their movement is constant. Where they meet, something has to give. In the case of the Kermadec Trench, the Pacific plate is sliding beneath the Indo-Australian plate, descending into the mantle at a steady angle. As it sinks, it drags the seafloor down with it, creating a trench that is not carved but pulled open. This process is called subduction, and while the term sounds technical and tidy, the reality is anything but. Subduction zones are among the most violent regions on the planet. They generate earthquakes, fuel volcanic arcs, and recycle vast amounts of crust back into the Earth's interior. The Kermadec Trench marks the surface expression of this slow collision, a visible boundary where one part of the planet disappears beneath another. The ocean does not simply cover this process, it participates in it. As the seafloor approaches the trench, it begins to bend, sediments compress, faults form. Small earthquakes ripple through the crust long before any major event announces itself. To instruments, this region is never still. Even in moments of apparent calm, strain is accumulating, energy is being stored, and pressure is building along boundaries that extend far below any point humans can directly observe. The trench is not a static feature frozen in time. It is an ongoing event. What makes this particularly unsettling is how little of it can be seen. On land, tectonic boundaries often leave visible scars. Mountain ranges rise. Fault lines cut across landscapes. Volcanoes announce their presence with smoke, ash and lava. In the ocean, much of this activity is hidden beneath kilometers of water. The trench forms silently, out of sight, its growth measured not by sight but by seismographs, sonar pulses, and indirect models built from sparse data. When scientists map the seafloor, they rely heavily on sound. Ships send sonar waves downward and measure how long it takes for them to bounce back. This data is then converted into depth maps, revealing the shape of the ocean floor. But even with modern technology, resolution decreases with depth. The deeper the trench, the more blurred the picture becomes. Fine details vanish, sharp edges soften. the trench becomes less a precise structure and more a suggestion, a dark streak in the data where certainty thins out. The Kermadec Trench stretches for more than 1,000 kilometres, forming part of a longer trench system that arcs across the South Pacific. Its depth varies along its length, with some sections plunging more steeply than others. This unevenness reflects the complexity of the subduction process. The plates do not slide smoothly. They lock, release, tilt, and fracture in response to forces that operate far below the seafloor. The result is a trench that is irregular, unpredictable, and constantly evolving. Standing at the edge of such a drop, if standing were possible, would feel fundamentally different from standing at the edge of a canyon on land. A canyon exposes its depth visually. The eye can trace its walls downward. The bottom, however distant, exists within sight. In the ocean, there is no such visual confirmation. The edge of the trench is defined not by what can be seen, but by what cannot. Beyond a certain point, there is only darkness and pressure, and the knowledge that the descent continues far longer than the intuition would suggest. This absence of visual cues plays a significant role in why trenches like Kermadec unsettle those who study them. Human perception relies on gradients, contrasts, and boundaries. Trenches erase these. The seafloor does not signal its drop dramatically. It simply begins to slope more steeply, and then more steeply still, until the slope becomes a plunge. Without instruments, the transition would be imperceptible. Without maps, the trench would be unknowable. Even with instruments, understanding remains partial. Submersibles descending into trenches often lose orientation. Downward feels the same as sideways in the absence of visual reference points. Navigation becomes an exercise in trust, relying entirely on data streams and calculations rather than instinct. This dependence on instruments introduces a psychological distance that is difficult to ignore. Every descent is mediated, filtered through screens and sensors that stand between human observers and the environment itself. The trench also disrupts the usual layering of the ocean. In most parts of the sea, water masses are stratified by temperature and salinity, creating layers that interact in predictable ways. Near trenches, these patterns can break down. Cold, dense water pools at depth. Currents behave differently. Sediments slide downward, carrying organic material from shallower regions into the abyss. This creates a slow rain of debris, feeding ecosystems that exist entirely without sunlight. But this feeding is uneven and unpredictable. The trench floor does not receive a steady supply. Instead, it experiences long periods of scarcity, punctuated by sudden influxes triggered by landslides or seismic activity. This instability shapes everything that lives there, favouring organisms that can survive long stretches of deprivation, and then rapidly exploit brief opportunities. The environment rewards patience and efficiency rather than speed or abundance. From a geological perspective, the trench is also a gateway. What descends here does not simply vanish. As the subducting plate sinks, it heats up, releases water, and interacts chemically with the surrounding mantle. These processes influence volcanic activity along the Kermadec Arc, a chain of volcanoes that rise above the ocean surface nearby. The trench and the volcanoes are connected parts of the same system, linked by movements and transformations occurring far below. This connection adds another layer of unease. The trench is not just deep, it is powerful. It plays a role in shaping earthquakes that can be felt hundreds of kilometers away. It contributes to volcanic eruptions that alter landscapes and atmospheres. Its influence extends beyond its physical boundaries, reminding scientists that what happens in the deep ocean does not stay there. And yet, despite its significance, the trench remains largely out of reach. Research expeditions are rare and expensive. Equipment failures are common. Data sets are incomplete. Every measurement carries uncertainty. Models must account for missing information, extrapolating from limited observations and accepting that large portions of the system remain invisible. This creates a persistent tension between what is known and what must be assumed. There is also the simple fact of scale. The depth of the Kermadec Trench is difficult to contextualize. Numbers alone fail to convey it. Even comparisons fall short. Saying it is deeper than the height of Everest inverted into the sea helps intellectually, but emotionally the scale remains abstract. The human brain evolved to navigate landscapes measured in meters and kilometers, not vertical voids stretching beyond the reach of light and pressure tolerance. As attention lingers on this place where the ocean falls away, a subtle shift occurs. The ocean is no longer a surface phenomenon with depth as a secondary attribute. Depth becomes the defining feature. The surface becomes distant, almost irrelevant. What matters is the downward direction, the pull of gravity amplified by water, the sense of descent that dominates every attempt to understand the trench. This is where the Kermadec Trench begins to separate itself from other deep-sea features. It is not merely deep water over flat ground. It is a structural break, a boundary where the planet reorganizes itself vertically. Studying it requires not only technology, but a willingness to accept that some environments resist full comprehension, not because they are mysterious in a romantic sense, but because they operate at scales and conditions that strip away human advantage. As this understanding settles in, the trench stops feeling like a location and starts feeling like a process, a place defined less by coordinates and more by motion, a descent that never quite finishes, a reminder that beneath the apparent stability of the ocean lies a dynamic system constantly reshaping itself, and as attention drifts further downward, toward regions where pressure increases and light has long since vanished, the realization grows that the fall has only just begun. Maps give us comfort. They flatten the world into something legible, something that can be understood at a glance. Coastlines become clean curves. Oceans become open spaces filled with labels rather than uncertainty. Even the most remote regions feel tamed once they're framed by borders, grid lines and names printed in calm, authoritative fonts. But some places resist this comfort more than others, and the Kermadec Trench is one of them. It exists on maps, clearly marked and measured, yet it never quite feels contained by them. To find the trench, most people begin with a familiar anchor point. New Zealand sits comfortably on many world maps, isolated but recognisable, its two main islands standing out against the blue of the South Pacific. From there, the eye drifts northeast, away from populated land and toward open ocean. Shipping routes thin out, labels become sparse. The water seems to stretch endlessly, uninterrupted by islands or landmarks that suggest human presence. It is in this quiet expanse that the Kermadec Trench runs like a long, narrow shadow. On a political map, the trench barely registers. There are no borders drawn around it, no capital cities nearby, no roads leading toward it. It does not belong to any nation in the way land does. It exists beyond the usual framework of ownership and governance, governed instead by international law that treats the deep ocean as a shared but largely inaccessible domain. This lack of political context makes it feel detached, as though it exists outside the human world entirely. Switch to a physical map, and the trench becomes easier to spot but no less unsettling. Bathymetric maps use colour gradients to show depth, shifting from light blues in shallow coastal waters to darker blues as depth increases. Somewhere east of New Zealand, the gradient darkens abruptly. Blues turn almost black. Contour lines crowd together, signalling a steep descent rather than a gradual slope. This sudden compression of depth is the trench's signature. It is the visual equivalent of a cliff edge, but one hidden beneath kilometres of water. Even here, though, the map only tells part of the story. The trench appears as a narrow feature compared to the vastness of the surrounding ocean, a thin scar rather than a broad chasm. This can be misleading. In reality, the trench is wide enough to swallow entire mountain ranges, and its walls descend at angles that would feel extreme on land. The apparent narrowness is a consequence of scale, a reminder that maps prioritise horizontal distance over vertical drama. Globes tell a slightly different story. When the Earth is rendered as a sphere rather than a rectangle, the isolation of the trench becomes more apparent. It sits far from continental masses, suspended between tectonic plates, rather than nestled against them. The curvature of the globe emphasises how remote this region truly is. There is no nearby landmass casting a shadow of familiarity. The trench occupies a part of the planet where human presence thins almost to nothing. Digital maps allow for deeper exploration, at least in theory. Zooming in reveals more detail, more labels, more data layers. Satellite imagery shows the ocean surface above the trench, indistinguishable from any other stretch of open water. There are no surface signs of what lies below, no discoloration, no ripples that hint at the depth beneath. The sea above the trench looks calm, even ordinary, reinforcing the unsettling idea that extreme environments can hide beneath benign appearances. Toggle on a tectonic plate map and the trench's purpose begins to emerge. Lines appear showing the boundaries between plates, and the trench aligns precisely with one of these boundaries. The Pacific plate moves westward here, diving beneath the Indo-Australian plate in a process that has been ongoing for millions of years. On the map, arrows indicate direction and speed, measured in centimetres per year. The numbers seem small, almost trivial, but they represent immense forces acting continuously across geological time. This is one of the strange tensions of mapping the trench. On the one hand, everything about it can be quantified. Its length, its maximum depth, its orientation, its relationship to plate boundaries. On the other hand, these quantifications struggle to convey what the trench actually represents. A map can show where the ocean floor drops, but it cannot communicate what it means for the planet to fold in on itself along that line, recycling crust into mantle and releasing energy in the process. Historical maps make this limitation even clearer. Early nautical charts showed the Pacific as an expanse of mystery dotted with conjectural coastlines and speculative islands. Depth measurements were rare and unreliable, taken with weighted lines that could only reach so far. Trenches did not exist on these maps because the technology to detect them did not yet exist. The ocean floor was imagined as relatively flat, a simple basin rather than a complex landscape. It was only with the development of echo-sounding in the early 20th century that the true shape of the seafloor began to emerge. Sound waves replaced ropes, allowing ships to measure depth quickly and repeatedly as they travelled. Gradually patterns appeared. Mid-ocean ridges, continental shelves, and eventually trenches. These features forced a revision of how scientists understood the ocean, transforming it from a passive container into an active participant in Earth's geological processes. Even so, early bathymetric maps were coarse. Trenches appeared as vague depressions rather than sharply defined features. It took decades of additional surveys, combined with advances in sonar resolution and satellite altimetry, to refine these images. Today's maps of the Kermadec Trench are far more detailed than those of a century ago, yet they remain incomplete. Large sections have been mapped only at low resolution, their finer features still inferred rather than observed. This incompleteness matters because the trench is not uniform. Its depth varies along its length. Its walls are fractured and uneven. Sediment accumulates in some areas while other sections remain bare rock. Faults cut across its structure at different angles, influencing how stress builds and releases. These details influence everything from earthquake behaviour to biological habitats, yet many of them remain poorly resolved on existing maps. There is also the issue of perspective. Most maps are created for surface navigation, not vertical exploration. Depth is treated as an attribute rather than a primary dimension. This reflects human priorities. We live on the surface, travel across it, and build infrastructure upon it. Depth, especially extreme depth, becomes secondary, something to be noted but not fully engaged with. Trenches challenge this perspective by demanding that depth be taken seriously. When scientists focus specifically on trenches, they often turn to specialized representations. Cross-sectional diagrams slice through the earth, showing the trench as a dramatic notch where one plate dives beneath another. These diagrams emphasize vertical relationships, making the trench feel more tangible. They also highlight how deep the subducting plate extends, descending hundreds of kilometers into the mantle long after it disappears from view at the trench itself. Still, these diagrams are abstractions. They simplify complex three-dimensional processes into two-dimensional slices. They assume uniformity where none exists and smooth curves where reality is jagged. They are tools for understanding, not mirrors of reality. The trench itself remains stubbornly resistant to full depiction. There is something psychologically disorienting about locating such a place on a map. Knowing exactly where it is does not make it feel closer. In fact, it can have the opposite effect. The clearer its position becomes, the more apparent its remoteness feels. It sits within reach of coordinates, but far beyond reach of experience. You can point to it, measure it, describe it, and still never come close to grasping what it is like to exist there. This disconnect is part of why the Kermadec Trench continues to trouble scientists. It occupies a strange position in human knowledge. It is not unknown in the sense of being unmapped or unmeasured. It is known in outline but unknown in detail. It is familiar in theory but foreign in practice. Maps give it a place in the world, but they do not domesticate it. There is also a subtle but important difference between seeing the trench as a destination and understanding it as a boundary. On maps, it can look like a feature you might travel to, a point of interest marked in the ocean. In reality, it is more accurately described as a transition zone, a place where one part of the planet becomes another. It marks the edge of a process rather than the centre of a location. This distinction matters because it reframes how scientists think about the trench. It is not just a deep hole to be explored, it is a site of interaction between systems that operate on vastly different scales. Plate tectonics, ocean circulation, seismic activity, and deep-sea ecology all intersect here. Maps can show these intersections conceptually, but they cannot capture their dynamic nature. The trench also challenges assumptions about accessibility. On land, mapping often precedes exploration. Roads follow mapped routes. Settlements grow where maps suggest resources or strategic advantages. In the deep ocean, mapping does not lead so easily to presence. Knowing where the trench is does not make it easier to reach. The cost, risk, and technical difficulty of deep-sea exploration remain formidable barriers. As a result, the Kermadec Trench exists in a kind of cartographic limbo. It is there on the map, undeniable and precisely located, yet functionally distant. It reminds scientists that knowing where something is does not necessarily mean knowing it. Location is only one aspect of understanding, and in environments this extreme, it may be the least informative one. This realization subtly alters how the map is read. The trench stops being just a line or a gradient and starts to feel like a question mark embedded in the sea floor. A reminder that even with satellites orbiting above and sensors probing below, the planet retains regions that resist full comprehension. The map shows the trench's outline, but what happens within that outline remains largely concealed. As attention lingers on this remote stretch of the South Pacific, the mind begins to drift downward again, away from coordinates and contours and toward conditions, toward pressure, darkness, and the physical realities that make the trench so difficult to approach. Locating the trench on the map is only the first step. Understanding what it means to descend into it requires letting go of the flat perspective entirely, and accepting that some places are defined less by where they are and more by how profoundly they alter everything that enters them. Depth is a word that feels familiar until it isn't. We use it casually, almost lazily. a deep thought, a deep breath, deep water. In daily life, depth rarely challenges us. It suggests something a little more intense, a little harder to reach, but still within the range of normal experience. The ocean, however, has a way of stripping that comfort away. It turns depth from a descriptive word into a physical reality, one that carries consequences the deeper you go. At the shoreline, depth feels optional. You can wade in, step back, choose how far you're willing to go. Even a few meters out, you can still see the bottom. Sunlight reaches down easily. Sound behaves normally. The water presses gently against your body, noticeable but not threatening. This is the depth most humans experience, and it sets the baseline for how we imagine the ocean. Beyond this, imagination often fills in the rest with vague darkness and silence, without grasping the scale involved. As depth increases, small changes accumulate quietly. Light begins to scatter differently. Reds fade first, then oranges and yellows, until everything takes on a muted blue-green tone. By around 200 meters, sunlight has gone entirely. This is the point where the ocean stops being visually intuitive. Below this, the human eye no longer helps. Cameras take over, bringing back images that feel detached, framed by artificial light and surrounded by blackness. For many divers and oceanographers, this zone already feels deep enough. It represents a threshold beyond which the ocean becomes something other than a place humans can inhabit directly. But in the context of the open ocean, 200 meters is barely a surface layer. Below it lie kilometers of water, stacked one atop another, each layer adding pressure, cold, and isolation. Pressure is the first truly unsettling factor. It increases relentlessly, indifferent to human tolerance. At 10 meters, pressure doubles compared to the surface. At 100 meters, it is already 11 times greater. At 1,000 meters, it reaches 100 times atmospheric pressure. These numbers are easy to read and difficult to feel. The human body is not built to register pressure directly. Instead, it registers failure. Lungs collapse, blood chemistry changes, cavities compress. At extreme depths, survival is not a matter of discomfort, but of structural integrity. Submersibles descending into the deep ocean are built with this in mind. Their hulls are often spherical, not for elegance but for survival. A sphere distributes pressure evenly, reducing points of weakness. Even so, every descent involves risk. Tiny flaws become catastrophic under thousands of tons of force. Metal fatigues, seals fail, acrylic windows, thick as walls, flex inward under pressure that never lets up. For scientists watching from the surface, this knowledge lingers in the background. Every meter downward increases not just depth, but consequence. There is no gradual adaptation zone for machines. They either withstand the pressure, or they do not. The deeper the target, the thinner the margin for error. Then there is distance. Depth is not just vertical measurement, it is separation. A submersible at 6,000 meters is not simply far below the surface, it is isolated from it. Communication becomes slower and less reliable. Radio waves cannot penetrate seawater, so communication relies on sound, which travels slowly and imprecisely. Commands take time to reach their destination. Data takes time to return. If something goes wrong, help is not on the way. It is effectively unreachable. This isolation alters how deep exploration feels compared to space exploration, despite superficial similarities. Astronauts orbiting Earth remain within constant communication. Rescue missions, while difficult, are theoretically possible. In the deep ocean, rescue becomes a near impossibility beyond certain depths. The ocean does not allow for rapid response. It absorbs sound, blocks signals, and resists intrusion at every level. Cold compounds this sense of hostility. Below the sunlit layers, temperature drops sharply and then stabilizes near freezing. This cold is not seasonal. It does not fluctuate. It exists as a constant background condition, slowing chemical reactions and biological processes alike. Materials behave differently. Batteries drain faster, lubricants thicken, electronics become brittle. Every system must be designed to function in an environment that never offers relief. Darkness, too, behaves differently at extreme depths. It is not the absence of light you experience in a dark room, where your eyes eventually adjust. It is absolute. Without artificial illumination, there is nothing to see no matter how long you wait. This darkness is not dramatic or mysterious in a cinematic sense. It is simply total, a physical condition that erases visual reference entirely. Psychologically, this matters more than it might seem. Humans rely on visual cues to orient themselves. In their absence, space becomes abstract. Direction loses meaning. Up and down blur into concepts rather than sensations. For crude submersibles, this disorientation is mitigated by instruments, but it never disappears entirely. For uncrewed vehicles, it manifests as navigational uncertainty, reliance on algorithms, and the ever-present risk of misjudging distance or orientation. At this point, depth stops being impressive and starts becoming uncomfortable. It is no longer about curiosity alone. It is about thresholds. How much pressure can materials tolerate? How much isolation can systems endure? How much uncertainty can scientists accept before the risks outweigh the potential knowledge gained? And then there are trenches. Ocean trenches represent a different category of depth altogether. They are not just deep regions of the ocean. They are extreme deviations from the surrounding seafloor, places where depth increases rapidly and dramatically over short horizontal distances. The descent into a trench is steeper, faster, and less forgiving than the gradual deepening found elsewhere. The Kermadec Trench belongs to this category. Its deepest sections plunge beyond 10,000 metres, a depth that defies easy comparison. At this point, pressure exceeds 1,000 atmospheres. Temperature hovers just above freezing. Darkness has been absolute for kilometres. This is the Hadal Zone, named after the Greek underworld, a label that reflects both its depth and the unease it inspires. What makes this depth particularly frightening is not just the numbers, but how little margin exists. There is no deeper place to retreat to if something goes wrong. There is no buffer. At these depths, systems operate at their absolute limits. Any failure is final. Any miscalculation is unforgiving. Even unmanned exploration becomes risky. ROVs and landers descending into trenches must survive not only pressure, but impact. Navigating uneven trench floors without visual reference increases the chance of collision. Sediments can obscure sensors. Currents behave unpredictably near steep walls. A vehicle that becomes entangled or damaged cannot be retrieved easily if at all. This reality forces scientists to confront an uncomfortable truth. There are depths beyond which observation becomes an act of acceptance rather than control. Data collection becomes opportunistic rather than systematic. Instruments are deployed, left to function autonomously, and then recovered if possible. Success is measured not by completeness, but by survival. The fear associated with extreme depth is not primal in the way fear of predators or heights might be. It is intellectual. It arises from understanding. Scientists know exactly what happens at those depths. They know the physics. They know the engineering limits. They know how small the margin for error is. The fear comes from clarity rather than mystery. There is also the unsettling realization that depth has no inherent stopping point. The ocean floor does not care how deep is too deep for humans. Trenches represent places where the planet continues downward regardless of human capacity to follow. They are reminders that the Earth is not scaled for us. We're adapted to a thin layer on its surface, and anything beyond that layer requires translation, mediation, and compromise. As depth increases, the environment becomes less forgiving not only physically, but conceptually. Time behaves differently. Missions are constrained by battery life, not by human endurance. Observations are brief and fragmented. Context is limited. A camera may capture a few square meters of seafloor, illuminated for seconds or minutes, and that snapshot becomes representative of an environment that spans hundreds of kilometers. This fragmentary nature of deep-sea knowledge contributes to unease. Scientists prefer systems they can observe repeatedly, under varying conditions, to build robust models. Trenches resist this approach. They are too deep, too remote, and too expensive to study continuously. Each descent offers a glimpse, not a narrative. Patterns must be inferred from sparse data, increasing uncertainty. Depth also complicates biological assumptions. Life persists in trenches, but it does so under conditions that challenge established ideas about energy availability, metabolism, and reproduction. Organisms live under pressures that would crush surface-dwelling species instantly. Their biochemistry operates differently. Their cellular structures are adapted to conditions that feel almost incompatible with life, as humans understand it. This raises unsettling questions. If life can exist there, under those conditions, what else might be possible elsewhere? Depth becomes not just a physical dimension, but a conceptual one, expanding the range of environments scientists must consider when thinking about habitability, resilience, and adaptation. At some point, depth stops being impressive and starts becoming humbling. It reveals the limits of human-centered thinking. It exposes how narrow the range of conditions humans are comfortable with, and how vast the range of conditions the planet supports without regard for that comfort. The fear that emerges at extreme depths is therefore not about monsters or unknown threats. It is about vulnerability. It is about recognizing that beyond certain thresholds, humans lose their advantage. Technology helps, but it does not erase the fundamental imbalance between human capability and environmental force. As attention continues downward, past familiar depth markers and into regions defined by pressure and isolation, it becomes clear that fear is not the right word so much as respect. A respect grounded in numbers, engineering constraints, and experience. A respect that acknowledges that some parts of the planet are not meant to be entered casually, or frequently, or at all. And still, the descent continues, because curiosity persists even in the face of discomfort. Scientists push deeper, not because it feels safe, but because understanding requires confronting boundaries. Depth, in this sense, becomes a measure not just of distance, but of how far humans are willing to go to understand their own planet. Pressure is one of those forces that is easy to ignore because it is everywhere. At the surface of the Earth, it presses down constantly, quietly, without sensation. The atmosphere weighs on every square centimetre of the body, yet it feels like nothing because the body evolved within it. Bones, tissues, and fluids balance it naturally. Breathing works, blood flows. Nothing feels compressed or strained. Pressure, at this level, is invisible and benign. The ocean changes that relationship almost immediately. Water is far denser than air, and it does not forgive depth. Every metre downward adds weight, not metaphorically but physically. Water stacks on water, layer after layer, until the force becomes something that no human body, no matter how trained, can withstand. Unlike temperature or light, pressure does not fade in or out. It accumulates relentlessly, indifferent to comfort or intention. At 10 metres below the surface, pressure has already doubled compared to sea level. For recreational divers, this is noticeable but manageable. Ears must equalise. Breathing becomes slightly more laborious. Equipment compensates for the change. At 30 metres, nitrogen begins to behave differently in the bloodstream, introducing the risk of narcosis. Judgment can dull. Reaction times slow. The environment starts to interfere with cognition itself. By 100 metres, humans are well outside natural limits. specialized gas mixtures become mandatory. Decompression schedules grow complex and unforgiving. The margin for error narrows sharply. Pressure is no longer just a physical force acting on the body. It becomes a constraint shaping every decision, every movement, every second spent below. These depths, however, are still trivial compared to what lies below. At 1,000 meters, pressure reaches 100 atmospheres. This is equivalent to placing the weight of a small car on an area the size of a postage stamp. At this level, no human can survive exposure. No amount of training or adaptation changes that. The body is simply not designed to resist such force. Beyond this point, exploration depends entirely on technology. Submersibles and remotely operated vehicles become the only way to enter the deep. Their design reflects an understanding that pressure is the primary enemy. Hulls are thick, shapes are rounded. Materials are chosen not for flexibility, but for resistance to collapse. Every joint, every seal, every viewport is a potential failure point under pressure that never lets up. As depth increases further, pressure does not merely threaten to crush, it infiltrates. Microscopic imperfections in materials become pathways for intrusion. Water molecules are forced into spaces they would never occupy at the surface. Electrical insulation degrades. Lubricants behave unpredictably. Metals fatigue under constant stress. Pressure is not a sudden impact. It is a continuous load, pressing inward without pause. At 5,000 meters, pressure exceeds 500 atmospheres. At 10,000 meters, it surpasses 1,000. These numbers are often quoted, but they remain abstract until translated into consequences. Acrylic windows, even those many centimeters thick, visibly deform under such conditions. Steel yields. Ceramics crack. Composite materials must be tested repeatedly because theoretical strength does not always predict real-world behavior under extreme pressure. One of the most unsettling aspects of pressure at these depths is how quietly it acts. There is no warning sound, no gradual build-up that can be sensed intuitively. Failure happens suddenly and completely. A hull that holds for hours can collapse in milliseconds if a critical threshold is crossed. When implosion occurs, it is not dramatic in a cinematic sense. It is instantaneous, violent, and final. Scientists who work with deep-sea vehicles understand this intimately. Every descent is accompanied by calculations, stress models, and safety margins, yet uncertainty remains. Materials behave differently under prolonged exposure. Repeated dives introduce fatigue. Small manufacturing variations can matter. Pressure does not care about intent or preparation. It responds only to physics. This is why trenches occupy a special category of concern. The Kermadec Trench is not simply deep. It pushes pressure to the extreme limits of what current technology can endure. Vehicles designed for abyssal depths may not be rated for Hadal ones. Instruments tested at 6,000 meters may fail at 10,000. Each additional kilometer downward multiplies stress rather than adding to it linearly. Pressure also alters chemistry in ways that are still not fully understood. At extreme depths, chemical reactions can proceed differently. Gases dissolve more readily into liquids. Proteins behave differently. Biological membranes must adapt to forces that would destabilize surface-dwelling organisms. This has profound implications for life, forcing it to evolve structures and processes that remain unfamiliar to scientists. Deep-sea organisms living under such pressure cannot tolerate decompression. Bringing them to the surface intact is nearly impossible. Cells rupture, tissues degrade. What survives the ascent often does so in altered form, stripped of the very adaptations that made survival at depth possible. This makes direct study extraordinarily difficult. Much of what scientists know about deep-sea life is inferred rather than observed in its native state. Pressure also complicates geological processes. Sediments behave differently when compressed under kilometers of water. Pore spaces shrink. Fluids are trapped. Chemical gradients form under conditions that do not exist closer to the surface. In subduction zones like the Kermadec Trench, pressure interacts with temperature to influence how rocks deform, fracture, and melt. These processes affect earthquake dynamics and volcanic activity far beyond the trench itself. For researchers, this creates an unsettling feedback loop. Pressure shapes the environment, but pressure also limits observation. The very force scientists want to study is the same force that prevents them from studying it easily. Instruments must survive long enough to collect data, yet deploying them introduces new variables. Pressure can alter sensor calibration. It can distort measurements. Data returned to the surface must be interpreted through the lens of conditions that cannot be reproduced exactly in laboratories. There is also a psychological weight to pressure, even when humans are not physically present. Watching a vehicle descend on a monitor, knowing that each passing minute increases the force acting on it, creates a quiet tension. Telemetry streams are scrutinized. Any anomaly feels amplified. A slight fluctuation in internal pressure readings can signal the beginning of failure or nothing at all. Uncertainty persists until the vehicle returns or does not. This tension is not dramatic. It is procedural. It lives in checklists, in cautious decision-making, in conservative dive profiles. Scientists working with trenches develop a different relationship with risk, one grounded in respect rather than bravado. Depth is not something to be conquered. Pressure makes that clear. Pressure also redefines scale. At the surface, structural strength is judged against gravity, wind, and weather. In trenches, gravity is almost irrelevant compared to hydrostatic force. A structure that would withstand extreme loads on land can fail instantly under deep-sea pressure. This inversion of priorities forces engineers to rethink assumptions that hold true everywhere else. Even sound behaves differently under pressure. Water density increases slightly with depth, affecting how acoustic signals travel. This influences communication, navigation, and mapping. Sonar pulses may bend or scatter in unexpected ways. Interpreting acoustic data from trench environments requires adjustments that add layers of uncertainty to already limited observations. The cumulative effect of all this is a sense that pressure is not just a physical condition, but a governing principle. It dictates what can exist, what can function, and what can be known. It narrows possibilities and enforces constraints without negotiation. Where pressure is extreme, compromise disappears. This helps explain why trenches inspire unease even among experienced scientists. The fear is not emotional in the traditional sense, it is analytical. It arises from understanding how close systems operate to failure, how unforgiving the environment is, and how limited human control becomes. Pressure removes flexibility. It replaces it with thresholds. Once those thresholds are crossed, there is no adaptation period, no opportunity to recover. Systems either endure or they do not. Life either evolves to function under those conditions or ceases to exist there. Exploration either succeeds briefly or ends abruptly. As attention lingers on this reality, it becomes clear that pressure is the defining feature of the deep ocean, more than darkness, more than cold. Darkness can be pierced with light. Cold can be managed with insulation. Pressure cannot be mitigated, only resisted. It is always present, always increasing, always waiting. This is why the descent into trenches feels qualitatively different from any other exploration humans attempt. It is not a journey into emptiness, it is a journey into force. A force so constant and overwhelming that it shapes everything within its reach, from the smallest microorganism to the strongest machine humans can build. And as depth increases beyond familiar limits, pressure stops being a variable and becomes a certainty. It is no longer something to measure, it is something to endure. Understanding this does not make the trench less intimidating, it makes it more honest. Pressure strips away illusion and leaves only physics behind. As the descent continues, pressure does not relax or stabilize. It continues to rise, quietly asserting itself with every meter downward. And with it grows the realization that the deepest parts of the ocean are not defined by what they contain, but by the immense, unyielding force that presses in on everything that dares to enter them. Darkness in everyday life is temporary. It arrives with the evening, recedes with morning, and even at its deepest it is softened by artificial light, distant street lamps, or the quiet glow of a screen. It is something we move through, something we expect to end. The darkness of the deep ocean is something else entirely. It does not arrive or depart. It simply exists, unchanged, uninterrupted, and absolute. As sunlight enters the ocean, it is immediately filtered. Water absorbs light selectively, stripping away colours one by one. Red disappears first, then orange, then yellow, until only blue remains. This happens within the first few tens of meters. By the time a diver reaches 100 meters, the world has already lost most of its familiar visual cues. Faces look pale, objects flatten into monochrome shapes, depth begins to feel less like distance and more like removal. Below 200 meters, sunlight is gone completely. Not dim, not faint, gone. This is the edge of the photic world, the last place where the sun has any influence. Everything below exists in a state of permanent night. No dawn has ever reached it. No dusk has ever passed through. This boundary marks more than a change in lighting conditions. It marks a transition between worlds shaped by entirely different rules. In the deep ocean, darkness is not an absence waiting to be filled. It is the default state. Light becomes an intrusion, a temporary disturbance introduced by passing organisms or human-made machines. When a submersible switches on its lamps, it does not illuminate a landscape that expects light. It imposes light onto an environment that has evolved without it for millions of years. The darkness surrounding the Kermadec Trench is older than humanity itself. Long before the first humans looked up at the night sky, long before memory, language, or recorded history, this darkness was already complete. It has remained uninterrupted through ice ages, mass extinctions, continental drift, and the rise and fall of species that never knew the surface world existed. This permanence changes how darkness behaves. It is not something the eyes adjust to. Human vision relies on contrast, edges, and gradients of light. In total darkness, these mechanisms fail. There is nothing to adapt to because there is nothing to see. Even time behaves differently. In darkness without reference points, seconds lose their shape. Movement becomes conceptual rather than perceived. For deep-sea exploration, darkness is more than an inconvenience. It is a structural condition. Cameras do not simply capture images, they construct them, pixel by pixel, within cones of artificial light that fade quickly into black. Beyond those cones, there is no context, no background, no horizon. Objects appear suddenly, fully formed, then vanish again just as abruptly. This lack of continuity makes interpretation difficult. On land, vision provides a sense of spatial relationship. A tree is seen against a forest. A building is understood in relation to streets and other structures. In the deep ocean, objects often appear isolated, floating in the black space. A rock, an organism, a piece of debris, all look similar at first glance because scale and surroundings are missing. Scientists reviewing footage from trench dives often describe a sense of visual dislocation. Even experienced observers struggle to judge size and distance. A small organism close to the camera can appear massive. A large feature further away can seem insignificant. Without ambient light, the brain has little to work with, and assumptions creep in unnoticed. Darkness also alters behaviour, particularly for the organisms that live within it. Many deep-sea species have no eyes at all. Vision is unnecessary where light never exists. Others have eyes that function differently, tuned not to sunlight, but to faint biological glows produced by other organisms. Bioluminescence becomes the only meaningful source of light, a language written in flashes, pulses, and glimmers. These biological lights are not decorative. They are tools. Some species use them to attract prey. Others use them to confuse predators. Some communicate. Some camouflage themselves by matching the faint, downwelling light from above, erasing their silhouettes when viewed from below. Even this faint light disappears entirely in the deepest trenches, forcing organisms to rely on other senses altogether. In the huddle depths, sound and chemical signals replace vision. Touch becomes important. Movement slows. Energy is conserved. Darkness shapes everything, from anatomy to behavior, because there is no alternative. There has never been light here to select for visual systems or rapid motion. Evolution has worked within the constraints of eternal night. For humans, this environment triggers a subtle discomfort that is difficult to articulate. Darkness on land can feel threatening because it hides unknowns. Darkness in trenches is different. It does not hide. It replaces. There is nothing behind it. No reveal waiting to happen. Just more darkness, extending indefinitely. This realization unsettles scientists not because it suggests danger, but because it removes familiar anchors. Exploration usually involves revealing something hidden, bringing it into the light. In the deep ocean, light does not reveal in the same way. It creates temporary islands of visibility in a sea of black, then leaves. The environment remains unchanged by the act of observation. There is also a temporal aspect to this darkness. Without light cycles, there is no day or night rhythm. Time does not structure itself visually. Organisms do not wake or sleep based on sunrise or sunset. Instead, biological rhythms are tied to other cues, such as food availability or internal clocks that operate independently of external light. For scientists, this complicates observation. Events cannot be contextualized within a daily cycle. Behavior observed at one moment may be entirely different at another, without obvious visual explanation. Patterns must be inferred from repeated visits separated by long intervals, each visit offering only a brief glimpse into a system that does not align with surface-based expectations. Darkness also affects memory. Human memory relies heavily on visual imagery. When experiences lack visual detail, they are harder to recall with precision. This makes describing deep-sea environments challenging even for those who have studied them extensively. Reports rely on instrumentation, measurements, and abstract descriptions rather than vivid recollection. There is a quiet irony here. The deeper scientists go, the more technologically sophisticated their tools become, and yet the sensory richness of the environment decreases. Data increases while experience diminishes. Numbers replace images. Graphs replace landscapes. Understanding becomes mediated through analysis rather than perception. This distance can create a strange emotional detachment. It is possible to study trench environments for years without ever feeling like one has truly been there. The darkness acts as a barrier not just to sight, but to familiarity. It prevents the formation of intuitive understanding, keeping the environment abstract and slightly unreal. Yet this darkness is not empty. It is full of matter, motion, and interaction. Particles drift downward, sediments settle, organisms move, feed, and reproduce. Geological processes continue. The absence of light does not mean absence of activity. It simply means that activity unfolds beyond human senses. In this sense, the darkness of the trench is not passive. It is active in shaping what exists there and how it can be studied. It selects against intrusion. It favours subtlety. It resists documentation. Every attempt to illuminate it feels temporary and incomplete. The age of this darkness adds another layer of unease. human history is measured in thousands of years. Even the earliest civilizations are recent compared to geological time. The darkness of the trench predates not only humanity, but most complex life. It has persisted through planetary changes that reshaped continents and climates alike. This continuity makes human presence feel brief and fragile by comparison. A submersible light switching on for a few hours is a blink in an environment defined by permanence. When the light turns off and the vehicle ascends, the darkness resumes exactly as it was before, unchanged and indifferent. Scientists are aware of this imbalance. It shapes how they think about exploration. There is no illusion of mastery here, no sense that repeated visits will domesticate the environment. Darkness ensures that the trench remains fundamentally other, no matter how much data is collected. As exploration continues deeper into the trench, darkness becomes more than a background condition. It becomes a defining feature of the experience. It frames every observation, limits every interpretation, and reinforces the sense that this environment operates beyond human-centered expectations. The deeper the descent, the more complete the darkness becomes. Artificial light grows weaker by comparison, its reach shrinking relative to the surrounding black. At extreme depths, even powerful lamps feel inadequate, their beams swallowed almost immediately. This is where darkness stops feeling like a lack and starts feeling like a presence. A constant enveloping condition that does not threaten but does not yield either. It does not respond to curiosity. It does not reward persistence. It simply exists. And as attention lingers there, in that uninterrupted night far below the surface, it becomes clear that darkness is not merely something scientists must overcome to study the trench. It is something they must accept as part of what the trench is. A defining reality that cannot be removed, only briefly disturbed, before it closes in again and waits. For a long time, depth was treated as a boundary for life rather than a setting for it. Early oceanographers assumed that as pressure increased, temperature dropped, and light vanished, life would thin out and eventually disappear. This assumption felt reasonable. On the surface, life depends heavily on sunlight, moderate temperatures, and relatively stable conditions. Remove those supports, and ecosystems collapse. Or so it seemed. The deep ocean quietly disagreed. As exploration pushed farther downward, life did not vanish. It changed. Each new depth range revealed organisms that looked unfamiliar, behaved differently, and survived under conditions once thought incompatible with biology. Still, there remained an unspoken expectation that somewhere, finally, there would be a limit. A depth where chemistry, pressure, and energy scarcity would close the door completely. Trenches were expected to mark that limit. They did not. The Kermadec Trench lies within what scientists call the Hardal Zone, the deepest ecological zone in the ocean, stretching from roughly 6,000 metres to the deepest points of the seafloor. The name itself reflects early assumptions. Hadal, drawn from the Greek underworld, implied a place beyond life, a final descent into sterility. Yet repeated observations have shown that this zone is not empty. It's inhabited quietly and persistently by organisms that have solved problems humans are only beginning to understand. Life in the trench does not announce itself dramatically. There are no forests of coral or schools of fish sweeping past cameras. Instead, it appears slowly, often unexpectedly. A small crustacean scuttles across sediment. A translucent fish drifts into view, pauses briefly in the artificial light, then disappears. Microbial mats coat particles of organic debris. Each sighting feels tentative, as though the environment allows presence but not abundance. Energy is the central constraint here. Sunlight does not reach these depths, so photosynthesis is impossible. Almost all energy must arrive from above, carried downward in the form of sinking organic material. This slow rain of particles, often called marine snow, consists of dead plankton, fecal pellets, fragments of plants, and other biological debris produced in surface waters. Over thousands of meters, most of it is consumed or broken down, leaving only a fraction to reach the trench floor. This means that food supply is sparse and unpredictable. Long periods of scarcity are the norm. When food does arrive, it often does so suddenly, delivered by landslides, carcasses sinking from above, or sediment flows triggered by earthquakes. Life in the trench is shaped by this irregular rhythm. Organisms must be able to endure long stretches with little nourishment, and then capitalise quickly when resources appear. Adaptation to pressure is equally critical. At Hadal depths, pressure reaches levels that would destroy the cellular structures of surface-dwelling organisms. Proteins fold differently. Cell membranes become rigid. Chemical reactions slow or stop. Trench organisms counter this by altering their biochemistry. Their cell membranes contain different lipid compositions that remain flexible under pressure. Their enzymes are structured to function efficiently when compressed. Their internal chemistry is tuned to conditions that would be lethal elsewhere. One of the most striking examples of trench life comes from amphipods, small shrimp-like crustaceans that appear frequently in deep-sea footage. In trenches, they are often among the most abundant visible animals. Their bodies are soft, flexible, and well suited to high pressure. They feed opportunistically, swarming food falls when they occur, and dispersing again when resources are exhausted. Their success challenges assumptions about complexity and resilience. Size, speed, and strength matter less than adaptability and efficiency. Fish also exist at these depths, though they are rarer and more specialised. Hadal fish often lack swim bladders, which would collapse under pressure. Their skeletons are lighter. Their muscles are less developed. They move slowly, conserving energy. Their sensory systems are adapted to darkness, relying on touch, vibration, and chemical cues rather than vision. The presence of fish in trenches was once controversial. Some scientists argued that vertebrate life could not survive beyond certain pressure thresholds. Yet repeated observations have shown that this limit is not as strict as once believed. Fish have been documented at depths exceeding 8,000 meters, reshaping understanding of vertebrate tolerance and forcing revisions of long-held biological models. Microbial life pushes these boundaries even further. Bacteria and archaea inhabit trench sediments, living within compacted layers of mud and mineral particles. Some feed on organic matter delivered from above. Others exploit chemical gradients created by geological processes. These microorganisms operate at pressures and temperatures that would disrupt the molecular machinery of most known life forms. Studying these microbes is exceptionally difficult. Bringing samples to the surface alters them. Pressure drops, temperature changes, chemical balances shift. Many organisms do not survive the ascent, and those that do may not behave as they did at depth. As a result, much of what is known comes from indirect measurements and high-pressure laboratory simulations that attempt to recreate trench conditions. Even these simulations have limits. Replicating thousands of atmospheres of pressure for extended periods is technically challenging. Maintaining biological samples under such conditions without contamination or degradation requires specialized equipment. This means that trench life remains partly theoretical, inferred from genetic material, metabolic byproducts, and brief in situ observations. There is also the question of contamination. Human activity has reached even the deepest trenches. Studies have found traces of industrial chemicals, plastics, and other pollutants in trench organisms. These findings are unsettling not only because they reveal the extent of human impact, but because they complicate biological interpretation. Organisms are adapting not only to natural extremes, but to anthropogenic ones as well. This raises uncomfortable implications. If life can persist under crushing pressure, near freezing temperatures, complete darkness, and limited energy, then the range of environments considered potentially habitable expands dramatically. Trenches become analogues for extraterrestrial environments, such as subsurface oceans on icy moons. Studying trench life is no longer just about understanding Earth. It becomes a test case for biology under extremes. At the same time, trench ecosystems are fragile. Their slow pace of life means recovery from disturbance takes a long time. A single disruptive event can alter conditions for decades. This fragility contrasts with their resilience to physical extremes, creating a paradox. These organisms withstand conditions that destroy machines, yet they are vulnerable to changes introduced from above. There is also the matter of scale. Life in trenches operates on different temporal rhythms. Growth is slow. Reproduction is infrequent. Population changes occur over long periods. This makes detecting trends difficult. Short-term studies may miss significant patterns simply because not enough time has passed. For scientists, this demands patience and humility. Trench ecosystems cannot be rushed into revealing themselves. They resist experimentation. They tolerate observation only briefly. Knowledge accumulates slowly, piece by piece, often through inference rather than direct measurement. The existence of life where life was not expected forces a re-evaluation of boundaries. It suggests that habitability is not defined by comfort, but by possibility. Conditions that feel extreme to humans may be merely challenging to organisms shaped by them over evolutionary timescales. This realization does not make the trench less intimidating. It makes it more complex. The trench is no longer just a hostile environment to be endured by machines. It is an ecosystem, sparse but real, shaped by forces that operate beyond human intuition. As attention lingers on these organisms, it becomes clear that their presence is not an anomaly. It is a consequence. The planet produces environments, and life responds, not by retreating, but by adapting in ways that stretch the definition of what living systems can be. This understanding shifts the emotional tone of trench exploration. Fear gives way to cautious respect. The trench is not empty or dead. It is selective. It allows only those forms of life that can meet its demands, and it enforces those demands without exception. As exploration continues deeper into the Hadal zone, each new observation reinforces the same message. Life does not require familiarity. It requires opportunity. Even in a place defined by pressure, darkness, and scarcity, opportunity exists, and life, given enough time, finds a way to occupy it. The trench, once imagined as a final boundary, becomes something else entirely. A reminder that the planet is not arranged around human expectations, and that existence, when stripped of comfort and abundance, can still persist in forms both quiet and astonishing. As the descent continues past familiar depth ranges and into the Hadal zone, life does not merely persist. It becomes unfamiliar in ways that challenge surface-based intuition. Creatures here are not dramatic in the sense of sharp teeth or aggressive behavior. They are strange because they operate under rules that feel inverted. Everything about them reflects compromise with pressure, darkness, and scarcity rather than competition or speed. The Hadal zone begins around 6,000 meters below the abyssal plains and extends down into the deepest trenches on the planet. This is where the environment stops resembling anything humans evolved alongside. Temperature stabilizes near freezing, light is absent. Pressure climbs into ranges that collapse conventional structures. Energy input becomes sporadic and unreliable. Under these conditions, evolution favors traits that look almost counterproductive by surface standards. One of the most frequently observed inhabitants of this zone are amphipods. At first glance, they resemble oversized shrimp, but their bodies tell a deeper story. They lack rigid exoskeletons, instead relying on softer, more flexible structures that do not fracture under pressure. Their internal chemistry includes compounds that stabilize proteins and membranes, preventing them from deforming when compressed. This biochemical resilience allows them to thrive where more complex organisms struggle. Amphipods are opportunists. They do not hunt in the traditional sense. They wait. When organic material arrives, whether as a sinking carcass or a sediment slide rich in nutrients, they respond quickly. Footage from trenchlanders often shows dozens or hundreds of amphipods converging on bait within hours. Then, just as quickly, they disperse again, conserving energy until the next opportunity appears. This rhythm of long stillness, punctuated by brief activity, defines much of Hadal life. Fish in the Hadal zone are rarer and more elusive. When they do appear, they often look unfinished to surface observers. Their bodies are translucent or pale, musculature is reduced, movement is slow and deliberate. These fish lack swim bladders, which would implode under pressure, and instead rely on neutral buoyancy achieved through tissue composition. Their bones are less calcified, reducing brittleness in a high-pressure environment. Their faces can appear distorted, not because of deformation, but because facial structures that serve important functions at the surface become unnecessary here. Vision is limited or absent. Instead, these fish rely on mechanoreception, sensing vibrations and pressure changes in the water. This allows them to detect movement without light, an ability far more useful in perpetual darkness. Some Hadal fish exhibit elongated bodies and reduced fins, minimizing energy expenditure during movement. Others show enlarged sensory organs tuned to chemical cues, allowing them to detect food or other organisms from a distance. Every feature reflects trade-offs made under constraint. Nothing exists without purpose. Nothing is decorative. Beyond visible animals, the Hadal zone hosts an immense microbial world. Bacteria and archaea dominate trench sediments, forming communities that process organic matter slowly and efficiently. Some microbes rely on detritus sinking from above. Others exploit chemical reactions associated with geological activity, such as the release of methane or hydrogen from subducting plates. These microbial systems operate at pressures and temperatures that would disrupt cellular machinery in most known organisms. Their enzymes are pressure tolerant, their membranes remain functional under compression. Their metabolic pathways are adapted to scarcity rather than abundance. In many ways, these microbes represent the most successful life forms in the trench, not because they are complex, but because they are persistent. Studying these organisms is exceptionally challenging. Sampling disturbs them. Decompression alters their chemistry. Many do not survive transport to the surface, and those that do may no longer behave as they did at depth. This forces scientists to rely heavily on genetic analysis, examining DNA and RNA sequences to infer metabolic capabilities and evolutionary relationships. Genetic studies have revealed that many Hadal microbes are closely related to species found in shallower waters, suggesting that colonization of trenches occurred through gradual adaptation rather than sudden innovation. This challenges the idea that extreme environments require entirely novel life forms. Instead, it appears that existing lineages can stretch their tolerances over time, reshaping themselves incrementally to meet new demands. Some trench organisms exhibit gigantism, growing larger than their shallow water relatives. This may be a response to cold temperatures and low metabolic rates, allowing organisms to conserve energy over longer lifespans. Others remain extremely small, minimizing resource requirements. Size varies not according to a single rule, but according to what best balances energy use and survival probability. Bioluminescence, common in midwater depths, becomes less prominent in the Hadal zone. With no ambient light to contrast against, producing light offers limited advantage. Some organisms retain the ability, possibly for close-range communication or predator deterrence, but many do not. Darkness is complete enough that light becomes unnecessary rather than useful. The trench floor itself hosts specialized invertebrates, adapted to soft sediments and uneven terrain. Worms burrow slowly, feeding on organic particles embedded in the mud. Sea cucumbers process sediment methodically, extracting nutrients before expelling the rest. These activities happen at a pace that feels almost static to surface observers, yet over time they shape the structure and chemistry of the seafloor. One of the most unsettling aspects of hadal fauna is how fragile they appear outside their environment. Creatures that survive immense pressure collapse or disintegrate when brought to the surface. Their bodies are not weak, they are optimized for a specific set of conditions. Remove those conditions, and the adaptations become liabilities. This fragility complicates public perception. Images of deep-sea creatures often appear distorted or damaged because they were not meant to exist at surface pressure. This creates the false impression that hadal organisms are grotesque or malformed. In reality, they are precisely engineered by evolution for their environment, elegant within the constraints imposed upon them. The hadal zone also contains scavengers that specialize in detecting rare food falls. When a whale or large fish sinks into a trench, it creates a temporary oasis of abundance. These events can support entire communities for months or years. Amphipods, worms, bacteria and fish all participate, each occupying a role in breaking down the material and recycling nutrients. Such events are rare, but their impact is disproportionate. They inject energy into an otherwise sparse system, shaping population dynamics and evolutionary pressures. Organisms that can locate and exploit these events gain a significant advantage, reinforcing traits related to sensory detection and mobility. The isolation of trench populations raises questions about genetic exchange. Trenches are separated by vast stretches of abyssal plain. How organisms move between them remains unclear. Some species may disperse through larval stages carried by deep currents. Others may evolve independently within individual trenches, leading to subtle genetic divergence over time. This possibility of isolation adds another layer of complexity. Trenches may function as ecological islands, each hosting slightly different communities shaped by local conditions and geological history. The Kermadec Trench may host organisms found nowhere else, not because of dramatic barriers, but because depth itself limits movement. Human influence has reached even these depths. Studies have detected microplastics and industrial chemicals within hadal organisms. These contaminants arrive via sinking debris and sediment transport, integrating into trench ecosystems despite their remoteness. The presence of such materials highlights how interconnected the planet's systems are, and how no environment remains entirely isolated from surface activity. This intrusion introduces new variables. Organisms adapted to extreme natural conditions now face novel compounds they did not evolve alongside. The long-term effects are unknown. Given the slow pace of life in the hadal zone, changes may take decades or centuries to become apparent, complicating assessment and response. The strangeness of hadal creatures lies not in their appearance alone, but in what they represent. They demonstrate that life can operate under constraints far outside human comfort. They challenge assumptions about necessity, abundance, and efficiency. They reveal that complexity is not the only path to persistence. For scientists, each encounter with these organisms reinforces a sense of humility. The trench does not produce life that conforms to expectation. It produces life that fits its conditions exactly, without regard for aesthetics or familiarity. As observation continues, it becomes clear that the hadal zone is not a chaotic frontier, but a finely tuned system. Every organism present has survived a long filtering process, shaped by pressure, darkness, and scarcity, into forms that function quietly and efficiently. This realization does not remove the unease associated with the trench. It deepens it. The environment is not empty or hostile by accident. It is selective by design, enforcing rules that few can meet. Those that do are reminders that the planet supports a far broader range of existence than surface life suggests. And as attention shifts from individual creatures to the system as a whole, the trench begins to feel less like a place of absence and more like a place of constraint. a setting where life exists not in spite of conditions, but because it has learned to operate within them, reshaping biology itself to fit a world defined by pressure, darkness, and patience. Exploration usually follows a familiar pattern. A place is identified, access routes are established, equipment is refined, and over time, presence becomes routine. Mountains gain trails, deserts gain research stations. Even space, once unreachable, now hosts satellites and orbital platforms. The Kermadec Trench does not follow this pattern. It resists repetition. Every attempt to study it feels like a first attempt all over again, constrained by forces that technology can approach but never neutralize. The primary difficulty begins with depth, but depth alone does not explain the problem. Many parts of the ocean are deep, yet comparatively well studied. The issue with trenches is how many limiting factors stack on top of one another without offering relief. Pressure, darkness, cold, distance, terrain, communication limits, cost, and risk do not appear one at a time. They arrive together, reinforcing each other and narrowing the range of possible actions until exploration becomes an exercise in compromise. Pressure sets the baseline. Any equipment intended to reach trench depths must be designed to survive forces that increase steadily and never plateau. This requires thick pressure housings, rounded structures, and conservative safety margins. Each of these choices adds weight. Added weight increases launch complexity. Heavier vehicles require larger ships, stronger winches, and more fuel. Every design solution introduces secondary problems that must also be solved. Pressure also limits size. Large vehicles experience greater total force acting on their surfaces, increasing the risk of structural failure. This pushes engineers towards smaller platforms, but smaller platforms can carry fewer instruments, less power, and smaller cameras. Trade-offs become unavoidable. Improving one capability often weakens another. There is no configuration that maximizes everything at once. Darkness compounds these issues. Without ambient light, all observation depends on artificial illumination. Lights consume power, generate heat, and attract organisms that may interfere with sensors. Stronger lights improve visibility but shorten mission duration and increase system complexity. Weaker lights preserve energy but limit what can be seen. In the Hadal zone, visibility is always partial, always constrained, and always mediated. Cold introduces another layer of difficulty. Near freezing temperatures affect batteries, electronics, and mechanical systems. Chemical reactions slow. Materials become brittle. Lubricants thicken or fail entirely. Components that function reliably at the surface can behave unpredictably after hours in deep cold. Designing systems to operate continuously under these conditions requires extensive testing, yet testing at full pressure and temperature simultaneously is expensive and limited. Distance amplifies every failure mode. The Kermadec Trench lies far from major ports and research infrastructure. Reaching it requires long transits across open ocean, often through rough seas. Ships must be self-sufficient, carrying spare parts, technicians and supplies for extended periods. Any mechanical issue that arises far from shore must be solved on site or result in mission cancellation. Communication presents another fundamental barrier. Radio waves do not travel through seawater, forcing reliance on acoustic signals. Sound travels slowly and with limited bandwidth. Commands sent to deep vehicles are delayed. Data returns at a fraction of the rate scientists are accustomed to on land or in space. Real-time control is impossible. Operators must anticipate problems rather than respond instantly to them. This delay changes how exploration is conducted. Vehicles must operate autonomously for long periods, following pre-programmed instructions. Autonomy introduces risk. Unexpected terrain, currents, or obstacles can lead to entanglement or collision. Without immediate human intervention, small issues can escalate quickly. Designing software capable of handling every contingency remains an unsolved problem. Terrain itself poses challenges unique to trenches. The seafloor is not flat or predictable. Steep slopes, fractured rock, unstable sediments, and abrupt drop-offs are common. Navigating these features without visual context increases the risk of impact or burial. A vehicle descending too quickly can collide with the bottom before sensors register proximity. A lander placed on an incline may slide out of view or topple. Sediment behaves differently at depth. Fine particles can remain suspended longer, obscuring cameras and clogging intakes. Landslides triggered by seismic activity can bury instruments without warning. Even the act of landing can disturb sediment enough to degrade data quality for hours or days. This unpredictability makes precise placement difficult and repeatable experiments rare. The trench's geological activity adds further uncertainty. Subduction zones are seismically active by nature. Earthquakes occur frequently, many too small to be felt at the surface but capable of shifting sediments and altering local conditions. Instruments deployed for long-term monitoring risk damage or displacement. Retrieving them intact is never guaranteed. Cost underlies all of these challenges. Deep-sea exploration is expensive even under favourable conditions. Trench exploration multiplies those costs. Specialised vehicles, reinforced cables, large research vessels, and highly trained personnel are required. A single expedition can cost millions of dollars and yield only a handful of dives, each lasting a few hours at depth. This economic reality limits frequency. Scientists cannot return repeatedly to refine observations the way they can in more accessible environments. Each mission must be carefully planned, with clear objectives and minimal redundancy. Mistakes are costly. Opportunities for improvisation are limited. Knowledge accumulates slowly, constrained by budgets as much as by physics. Human presence adds another layer of complexity. Crude submersible dives to trench depths are extremely rare. The risk to human life is significant and rescue is not feasible. Most trench exploration relies on unmanned systems, which removes immediate danger to people but introduces other limitations. Machines do not notice subtle cues. They do not improvise intuitively. They do not form holistic impressions. They collect data, but understanding must be constructed later. Data interpretation itself is difficult. Measurements taken under extreme conditions may not translate cleanly to surface-based models. Sensors can drift. Calibration can change under pressure. Instruments may behave differently after repeated exposure. Separating signal from artifact requires careful analysis and often leaves room for doubt. Biological sampling is especially challenging. Organisms adapted to extreme pressure often do not survive ascent. Bringing samples to the surface alters their structure and chemistry, limiting what can be learned from them directly. In situ, experiments are possible but constrained by power, space, and time. Much of trench biology remains inferred rather than observed. There is also the issue of scale. Trenches are vast. The Kermadec Trench stretches for more than 1,000 kilometres, yet exploration typically covers areas measured in square metres. Each dive illuminates only a tiny patch of seafloor. Extrapolating from such limited coverage introduces uncertainty. Local conditions may not represent the trench as a whole. Weather at the surface influences everything below. Rough seas complicate deployment and recovery. Strong currents affect cable tension and vehicle stability. Operations may be delayed or aborted due to conditions that have nothing to do with the trench itself. Time windows are narrow, and missed opportunities may not return for years. Human factors also play a role. Fatigue, decision-making under pressure, and coordination among multidisciplinary teams all affect outcomes. Long expeditions strain crews physically and mentally. Mistakes are more likely when operations run around the clock in challenging conditions. Managing these risks requires experience and discipline, yet even the best teams face limits. Regulatory and ethical considerations add further constraints. Deep-sea environments are increasingly recognized as vulnerable ecosystems. Sampling must be conducted responsibly. Disturbance should be minimized. This limits the number and type of experiments that can be performed. Scientists must balance curiosity with stewardship, even when knowledge gaps remain large. All of this contributes to a persistent sense of difficulty that never fully diminishes. Unlike environments where familiarity breeds efficiency, the trench remains resistant to routine. Each expedition feels provisional. Each data set feels incomplete. Progress is real but incremental, measured in small advances rather than breakthroughs. The Kermadec Trench exemplifies these challenges. Its depth pushes equipment to limits. Its remoteness strains logistics. Its geological activity introduces risk. Its ecosystems resist easy sampling. Studying it requires patience, resources, and acceptance that uncertainty will remain. This difficulty is not a failure of science. It is a reflection of scale. The trench operates on dimensions that do not align with human convenience. Exploration here is not about conquest or mastery. It is about cautious entry, brief observation, and careful retreat. Understanding accumulates slowly, not because scientists lack skill or motivation, but because the environment dictates the pace. The trench allows only what it allows. It offers glimpses, not continuous access. It enforces boundaries that technology can approach but never erase. As attention moves forward, the realization settles in that difficulty itself is part of the trench's significance. It is not merely a place that is hard to reach. It's a place that reminds scientists of the limits of control, the costs of curiosity, and the patience required to study a planet that still holds regions fundamentally beyond easy reach. Loss in the deep ocean does not announce itself loudly. There are no headlines drifting across the water, no wreckage washing ashore to signal what has vanished. Most of what is lost in the depths disappears quietly, slipping out of reach without ceremony, often without witnesses. In places like the Kermadec Trench, loss is not an event, it is a condition. When people think about loss at sea, they often imagine shipwrecks, vessels swallowed by storms, explorers lost to miscalculation, artifacts resting on the seafloor like frozen moments in history. Those losses are real, but they represent only a small fraction of what the deep ocean takes and keeps. Far more significant are the losses that never make it into stories, losses that occur beyond visibility, beyond recovery, and often beyond awareness. Scientific equipment is among the most common casualties. Trench exploration operates at the edge of engineering tolerance. Landers fail to release ballast and never return. Cables snap under tension. Pressure housings develop microscopic fractures that become catastrophic at depth. Instruments are buried by sediment slides or shifted by seismic activity until they are no longer locatable. These losses are not dramatic, but they are frequent enough to shape how science is conducted. Each lost instrument represents more than financial cost. It carries with it unrealized data, unanswered questions, and interrupted experiments. Months or years of planning can end in silence when a system does not return. The ocean offers no explanation. It simply absorbs the failure and moves on, unchanged. There is also the loss of opportunity. Because trench expeditions are rare and expensive, every failed deployment means a long delay before another attempt can be made. Weather windows close. Funding cycles end. Teams disperse. Momentum is lost. In environments where repetition is key to understanding, this scarcity of access compounds uncertainty. Biological samples are another category of loss, though in this case the loss often occurs during retrieval rather than descent. Organisms adapted to extreme pressure rarely survive the journey back to the surface intact. Their tissues rupture. cellular processes fail. What arrives topside is often a distorted remnant of what existed at depth. The original organism in its functional state is effectively lost the moment it leaves its environment. This complicates interpretation. Scientists must reconstruct biology from fragments, genetic traces, and indirect measurements. Entire physiological processes remain inferred rather than observed. The true nature of trench life exists largely beyond direct human experience, preserved only in situ where it cannot be fully accessed. Some losses are less tangible, but equally significant. Context is often lost. A brief video clip of a creature or geological feature lacks the surrounding environmental information needed for full understanding. Temperature gradients, chemical conditions, population dynamics, and temporal variability are difficult to capture in short visits. Without context, observations risk being misleading or incomplete. There is also the loss of continuity. On land, long-term monitoring stations collect data year after year, building rich records of change. In trenches, such continuity is rare. Instruments may not survive long enough to generate extended time series. When they do, retrieval remains uncertain. Gaps in data become the norm rather than the exception. Human error contributes to loss as well. Deep-sea operations are complex, involving coordination between ships, vehicles, software systems, and crews. Miscommunication, miscalculation, or simple fatigue can lead to mistakes. In a forgiving environment, these mistakes might be corrected. In a trench, they often are not. There are also losses tied to restraint. Ethical considerations increasingly limit how much disturbance scientists are willing to cause in deep-sea ecosystems. This is a necessary and responsible shift, but it comes with trade-offs. Fewer samples are collected, experiments are scaled back. Some questions remain unanswered because answering them would require too much disruption. Beyond science, there are losses that reflect broader human impact. Industrial pollutants, plastics, and chemical residues have been found in trench sediments and organisms. These materials arrive unintentionally, carried by currents and sinking debris. Their presence represents a loss of isolation, the end of the idea that any place on Earth remains untouched by surface activity. This contamination complicates ecological baselines. Scientists struggle to determine what trench ecosystems looked like before human influence because direct observation began only after that influence had already spread. The original state of these environments may be permanently lost, replaced by a modified version whose history cannot be fully reconstructed. Cultural loss also plays a subtle role. The deep ocean has never been woven into human culture in the way land and sky have. There are no ancient myths rooted in trenches, no oral histories describing their depths. This absence means that when loss occurs there, it does not resonate culturally. It passes unnoticed, unmarked by memory or narrative. Even knowledge itself can be lost. Data stored on recovered instruments may be incomplete or corrupted. Hard drives fail. Files become unreadable. Formats become obsolete. Without careful preservation, years of work can fade into irrelevance. In extreme environments where data is scarce, such losses carry disproportionate weight. There is also the loss of immediacy. Studying trenches often involves long delays between observation and analysis. Samples take time to process. Data requires extensive validation. By the time conclusions are drawn, conditions may have changed. Events that could have been observed directly have already passed. Loss in the trench is therefore cumulative. It accrues through absence, delay, and limitation rather than catastrophe. It shapes scientific understanding not by what is known, but by what remains unknowable. This reality fosters a particular mindset among researchers. Expectations are tempered. Success is defined narrowly. A single functioning sensor can be considered a victory. A brief glimpse of an organism may represent years of progress. Loss becomes an accepted part of the process, not an exception. Yet acceptance does not eliminate frustration. Scientists are acutely aware of what remains out of reach. They know that entire communities, processes and interactions exist beyond their instruments' capabilities. They know that some answers may never be recovered, not because they are impossible, but because the environment exacts too high a price. There is also the emotional weight of knowing that loss is asymmetrical. The trench loses nothing when humans lose equipment or data. It does not degrade or diminish. The imbalance reinforces a sense of humility. Exploration here is not a dialogue between equals. It is a one-sided effort to extract meaning from a system that does not respond. Loss extends even to language. Describing trench environments often requires borrowing terms from other contexts, metaphors that only approximate reality. Without direct experience, language strains to keep up. Precision gives way to approximation. Some aspects of the trench resist description altogether. This linguistic limitation feeds back into understanding. What cannot be described clearly is harder to conceptualize, harder to study, harder to prioritize. The trench becomes abstract, defined by numbers and constraints rather than lived reality. This abstraction can lead to underestimation of its significance and vulnerability. Despite these losses, exploration continues, not because loss is ignored, but because understanding is still possible within constraints. Scientists adapt their methods, refine their tools, and accept partial answers. Knowledge advances slowly, shaped as much by what is missing as by what is found. In this sense, loss becomes informative. It highlights the boundaries of current capability. It reveals which questions are premature and which approaches require rethinking. It forces innovation, pushing engineers and scientists to design systems that minimize loss or extract more value from limited opportunities. The trench teaches through absence as much as presence. It demonstrates that not all environments yield easily to investigation, and that some knowledge may always remain incomplete. This does not diminish its importance. If anything, it enhances it. As attention drifts deeper into the trench, the accumulation of loss creates a quiet backdrop for everything else. It is not mourned, but it is felt. Each missing data point, each unrecovered instrument, each organism that cannot be studied alive adds to a sense that this environment exists largely on its own terms. Understanding what has been lost also clarifies what remains at stake. The trench holds processes that influence the entire planet, from seismic activity to carbon cycling. Losing the opportunity to understand these processes fully has implications beyond academic curiosity. It limits predictive ability. It increases uncertainty. Yet even here, loss does not end the story. It shapes it. It ensures that exploration of the deep ocean remains cautious, deliberate, and respectful. It reminds scientists that access is a privilege, not a right, and that some places demand patience rather than persistence. As the focus shifts forward, toward the forces that continue to act within the trench, loss lingers as a quiet companion. Not as failure, but as context. A reminder that in the deepest parts of the ocean, knowledge is always partial, presence is always temporary, and what remains unseen may always outweigh what is found. The seafloor beneath the open ocean can appear calm, even inert, when viewed from the surface. Waves pass overhead. Ships move quietly across it. Satellites register little more than subtle changes in elevation. But this stillness is misleading. Beneath the water, and especially beneath the trenches, the planet is never at rest. Motion is constant, tension is always accumulating, and release is inevitable. The Kermadec Trench exists because the Earth does not behave like a solid object. Its outer shell is broken into massive plates that drift slowly over the softer mantle below. These plates move at rates measured in centimetres per year, a pace that feels negligible until multiplied by millions of years. Over geological time, that slow motion becomes irresistible. Where plates meet, pressure builds. Something bends, fractures, or sinks. In this case, it sinks. Along the length of the Kermadec Trench, the Pacific Plate is being forced downward beneath the Indo-Australian Plate. This is not a smooth descent. The edges of the plates are rough, irregular, and uneven. As they slide past one another, they catch. Stress accumulates. Rock deforms elastically, storing energy like a compressed spring. For long periods, nothing visible happens. Then, without warning, the system fails. An earthquake is not the cause of motion here. It is the result of motion that has been resisted for too long. When the locked sections of the plates finally slip, energy is released in the form of seismic waves that travel through rock, sediment, and water alike. In trench environments, these earthquakes often occur far below the seafloor, invisible to human observers yet powerful enough to reshape the terrain. Many of these earthquakes are small, registering only on sensitive instruments. They occur constantly, marking the gradual adjustment of the plates as they move past one another. Others are larger, capable of triggering landslides, altering sediment layers, and changing the shape of the trench floor itself. The trench is not carved once and left behind. It is continuously reworked by these events. What makes this particularly unsettling for scientists is how little of this activity can be directly observed. Seismic networks on land can detect earthquakes, locate their epicenters, and estimate their magnitude, but the seafloor itself remains largely uninstrumented. Installing long-term seismic sensors at trench depths is technically difficult and risky. Many instruments do not survive long enough to provide extended records. As a result, much of what is known about trench seismicity comes from indirect evidence. Earthquake waves recorded thousands of kilometers away are traced back to their source. Models are constructed to estimate what must have happened along the plate boundary. These models are useful, but they are abstractions. They cannot capture every detail of a system that operates across vast depths and pressures. The seafloor responds to this tectonic activity in complex ways. Sediments accumulate slowly over time, settling into layers that record past events like pages in a book. Earthquakes disturb these layers, causing them to slump, fold, or collapse. Entire sections of the trench wall can fail, sending massive sediment flows downward into deeper regions. These flows reshape the seafloor and redistribute organic material, influencing deep-sea ecosystems in the process. Such landslides are not rare anomalies. They are part of the normal life cycle of a trench. Over long timescales, they play a major role in shaping its geometry. Steep walls become unstable, material moves downward, the trench deepens in some areas and fills in slightly in others, only to be pulled down again as subduction continues. This constant reworking creates an environment of instability. For life, this means living on terrain that may shift without warning. For instruments, it means operating in a landscape that does not stay fixed. A sensor placed carefully on the seafloor may be buried, tilted, or displaced by an event that occurs far from its location. Data streams can end abruptly, not because the instrument failed, but because the ground beneath it moved. The connection between earthquakes and trenches extends beyond the seafloor itself. When large earthquakes occur along subduction zones, they can displace vast volumes of water, generating tsunamis that propagate across entire ocean basins. While the Kermadec region has produced fewer widely destructive tsunamis than some other subduction zones, the potential remains. Energy released deep below can manifest far away, linking trench dynamics to surface impacts. Volcanism is another expression of this restless system. As the subducting plate descends, it heats up and releases water into the overlying mantle. This lowers the melting point of surrounding rock, generating magma that rises toward the surface. The result is the Kermadec volcanic arc, a chain of volcanoes that parallels the trench. Some remain submerged, others break the surface as remote islands, All are fed by the same deep processes that create the trench itself. This connection reinforces a critical idea. The trench is not an isolated feature. It is part of a larger machine, one that cycles material from the surface into the deep earth and back again. Earthquakes, volcanoes, and seafloor deformation are not separate phenomena. They are expressions of the same underlying motion. For scientists, this interconnectedness complicates interpretation. Observations made at the surface must be linked to processes occurring kilometers below. Signals are delayed, filtered, and transformed as they move through different materials. Separating cause from effect requires careful analysis and often leaves room for ambiguity. The trench environment also challenges assumptions about predictability. While plate motion is steady on average, stress accumulation and release are not. Earthquakes do not occur on schedules that align with human planning. An expedition may take place during a period of relative quiet or coincide with increased activity. Instruments deployed to measure background conditions may instead capture transient events that dominate the data. This unpredictability affects risk assessment. While deep-sea vehicles are not directly threatened by most earthquakes, secondary effects such as sediment movement and slope failure can pose serious hazards. A lander descending into the trench may encounter conditions that did not exist days or even hours earlier. Navigation plans based on previous maps may suddenly be outdated. There is also the challenge of scale. Earthquake processes occur over areas much larger than the footprint of any single instrument. A sensor records local motion, but that motion is part of a broader pattern extending along the plate boundary. Understanding the pattern requires integrating data from multiple sources, many of which are located far from the trench itself. This integration is further complicated by the depth of the system. Subduction zones extend hundreds of kilometers into the Earth. Processes occurring deep within the mantle influence behavior at the seafloor, but those processes are inferred rather than observed. Seismic waves provide clues, but interpretation depends on models that simplify complex realities. Despite these challenges, earthquakes offer rare moments of clarity. They act as probes, sending waves through the Earth that reveal information about its interior. Variations in wave speed and direction hint at temperature, composition, and structure. In this way, seismic activity becomes a tool for understanding regions otherwise beyond reach. Yet even this tool has limits. Resolution decreases with depth. Noise interferes with signals. Multiple interpretations remain possible. The trench yields information, but not certainty. For deep-sea ecosystems, seismic activity is both disruptive and generative. Landslides deliver nutrients to deeper regions. New habitats are created as rock surfaces are exposed and sediments redistributed. Over long timescales, this disturbance contributes to ecological diversity rather than eliminating it. Life adapts to instability, finding ways to persist within a moving landscape. This dynamic environment contrasts sharply with surface perceptions of the deep ocean as static and unchanging. In reality, trenches are among the most active geological environments on the planet. Their activity simply unfolds at depths that keep it out of sight. The restless nature of the seafloor reinforces a broader theme. The trench is not a destination with fixed characteristics. It is a process unfolding over time. Studying it requires not only advanced technology, but a willingness to accept that observations capture moments rather than states. Scientists working in these environments often speak of humility. Models are provisional, conclusions are tentative. New data can overturn assumptions built over decades. The trench teaches that stability is an illusion, especially at the boundaries where the planet reorganizes itself. As attention continues downward and outward, the sense of motion never fully disappears. Even in moments of apparent stillness, stress accumulates invisibly. The seafloor waits, not passively but dynamically, storing energy that will eventually be released. This understanding shapes how the trench is perceived. It is not just deep, it is active. It does not simply exist, it acts. And in acting, it reminds scientists that the Earth beneath the oceans is as alive with motion as the landscapes above, even if its movements unfold beyond easy reach or immediate awareness. The deeper this realization settles, the clearer it becomes that fear associated with trenches is not about sudden catastrophe. It is about constant tension. A recognition that beneath the calm surface lies a system in motion, reshaping itself continuously, indifferent to observation and governed by forces that operate on scales far larger than any single expedition or instrument can fully capture. Beneath the surface calm of the oceans, beneath even the restless movement of earthquakes and shifting plates, there exists a deeper level of activity that rarely enters everyday conversation. It is not loud. It does not announce itself with explosions or sudden fractures. It works slowly, continuously, and at scales that are difficult to visualize. The trench is one of the few places where this hidden machinery comes closest to the surface, offering subtle clues about processes that shape the entire planet. The Kermadec Trench is not merely a deep scar in the seafloor, it is a gateway. What disappears into it does not simply vanish. It enters a system that recycles the planet's outer shell, redistributes heat and material, and drives cycles that have been operating since long before continents took their current shapes. The trench is an entry point into the Earth's interior, a place where surface materials begin a long journey inward. At the most basic level, the trench marks where one tectonic plate slides beneath another. But this description, while accurate, understates the complexity involved. The descending plate carries with it sediments, seawater trapped in pores and cracks, organic material, and minerals formed at the surface. As it sinks, pressure and temperature increase steadily. Water bound within minerals is released. Chemical reactions occur. Rocks change phase. Density shifts. The plate does not remain the same object it was at the surface. This transformation matters because it influences everything above it. As water is released from the subducting plate, it migrates upward into the overlying mantle. Water lowers the melting point of mantle rocks, allowing magma to form more easily. That magma rises, feeding volcanoes that line the trench in arcs that trace the boundary between plates. The surface expression of this process may be a distant island volcano, but its origin lies deep beneath the trench. This is part of the planet's thermal regulation system. Heat generated within the Earth must escape somehow. Subduction zones and the volcanic arcs they support are among the primary pathways for that heat to move upward. Without these processes, the interior would behave differently, altering convection patterns and plate motion. The trench is therefore not an isolated feature. It is an integral component of how the planet manages energy. Material cycling follows a similar pattern. The Earth's crust is not permanent. It is created at mid-ocean ridges and destroyed at trenches. This recycling maintains a balance that has persisted for billions of years. Without trenches, the crust would accumulate without limit. Without ridges, it would disappear. The two work together, forming a system that keeps the planet's surface dynamic rather than static. The trench also plays a role in the long-term carbon cycle. Carbon enters the ocean through biological activity and chemical weathering on land. Some of it sinks to the seafloor as organic material or carbonate sediments. In subduction zones, portions of this carbon are dragged downward with the plate. Some is released back to the surface through volcanic activity. Some may remain locked in the mantle for millions of years. This slow exchange influences atmospheric composition over geological time. It helps regulate carbon dioxide levels, affecting climate on scales far beyond human history. The trench, silent and unseen, contributes to conditions that allow surface life to exist at all. This connection between deep processes and surface habitability is easy to overlook because it operates so slowly, but it is fundamental. Pressure and temperature increase steadily as the plate descends, but not uniformly. Variations in composition, water content, and structure create zones where reactions occur at different depths. These reactions affect seismic behavior. Some earthquakes originate deep within the subducting slab, far below the trench itself. Their existence reveals that brittle failure can occur under conditions once thought too extreme for it. These deep earthquakes offer clues about the physical properties of materials under immense pressure. By analysing seismic waves, scientists infer how rocks behave thousands of kilometres beneath the surface. In this way, the trench becomes a probe into the interior, transmitting information upward through vibrations that reach instruments on land. The geometry of the trench also influences mantle flow. As the plate sinks, it displaces mantle material, creating circulation patterns that extend far beyond the immediate boundary. These flows affect how heat and material move within the Earth, influencing the behaviour of neighbouring plates and distant regions over long timescales. Understanding these interactions requires models that integrate geology, physics, chemistry, and fluid dynamics. Each discipline offers partial insight. None alone can describe the system fully. The trench sits at the intersection of these fields, demanding collaboration and synthesis. Yet even with sophisticated models, uncertainty remains. Direct observation of these deep processes is impossible. Scientists rely on indirect evidence, laboratory experiments, and simulations. Each carries assumptions and limitations. The deeper the process, the more abstract the understanding becomes. This abstraction can create discomfort. There is a sense that something immensely powerful is operating just beyond reach, shaping the planet in ways that are only partially understood. The trench offers a glimpse, but not a full view. It is like seeing the surface of a machine without access to its interior components. The scale mismatch adds to this unease. Human lifespans are brief compared to geological processes. Plate motion measured in centimetres per year feels trivial until multiplied by millions of years. The trench deepens and migrates on timescales that dwarf human experience. Changes that are significant geologically may be imperceptible within a lifetime. This temporal distance complicates cause and effect. Events separated by millions of years are linked within the system, but those links are difficult to trace conclusively. Scientists reconstruct histories from incomplete records, piecing together sequences that are always provisional. The trench also interacts with the biosphere in subtle ways. Nutrients delivered to deep-sea ecosystems via sediment flows originate from surface productivity. Volcanic emissions influence ocean chemistry. Seafloor deformation alters habitats. These connections remind scientists that biological and geological systems are intertwined, not separate layers operating independently. Even the distribution of elements essential for life is influenced by subduction. Trace metals released from descending plates can enrich magmas and hydrothermal systems. These elements eventually enter oceans and soils, supporting biological processes. The trench contributes indirectly to the chemical diversity that life depends on. The hidden machinery does not operate smoothly. It jams, slips, and readjusts. Earthquakes represent moments when accumulated stress exceeds resistance. Volcanic eruptions release pressure built over long periods. These events are not failures of the system, they are how the system functions. For those studying the trench, there is a persistent awareness that they are observing outputs rather than mechanisms. Earthquakes are signals, volcanoes are expressions. The trench itself is a boundary condition. The actual machinery operates deeper still beyond the reach of drills or sensors. This distance fosters humility. Conclusions are framed cautiously. Language reflects probability rather than certainty. Models are updated as new data arrives. The trench resists definitive statements because it represents processes that cannot be isolated or simplified easily. There is also the recognition that these deep processes are not optional. They have shaped the planet's surface repeatedly, driving continental collisions, mountain building, and ocean basin formation. Without them, the Earth would be a very different place, likely less hospitable to complex life. The trench embodies this inevitability. It is not a feature that can be turned off or stabilized. It will continue to operate as long as the planet remains geologically active. Human observation is a brief interruption in a system that has no awareness of being watched. As attention rests on this deeper perspective, the trench begins to feel less like an anomaly and more like a necessary component. Its depth and remoteness are not excesses. They are consequences of how the planet works. This reframing alters how fear is understood. The unease associated with trenches does not arise solely from darkness or pressure. It arises from recognizing that beneath familiar landscapes lies a system of immense power operating continuously, indifferent to surface life yet essential to it. The hidden machinery of the planet does not seek balance in the way humans define it. It seeks equilibrium through motion, recycling, and transformation. Trenches are where that process becomes visible, not as spectacle, but as structure. Understanding this does not make the trench comforting, it makes it honest. It reveals that the planet is not a static stage for life, but an active participant in shaping conditions for existence. As exploration moves forward, this awareness lingers. Every descent into the trench is also a descent into the planet's inner workings. Each data point is a clue to processes that extend far beyond the seafloor, connecting the deep ocean to volcanoes, climate, and the long-term evolution of the Earth itself. The trench stands as a reminder that the most important systems are often the least visible, that beneath calm surfaces, complex machinery turns relentlessly, and that understanding our planet requires acknowledging not just what we can see, but what operates quietly, continuously, and far below our reach. Unease is not something scientists like to admit too easily. Training encourages distance, objectivity, and careful separation between emotion and observation. Data should speak louder than instinct. Models should replace intuition. Yet in places like the Kermadec Trench, unease persists, not as fear in the dramatic sense, but as a steady undercurrent that never quite disappears, no matter how familiar the equations or how refined the instruments become. Part of this unease comes from knowing exactly how little margin exists. At trench depths, everything operates close to failure. Pressure housings are tested to limits that cannot be exceeded. Cables are rated for loads that leave little room for error. Power systems are sized conservatively, not because engineers lack ambition, but because ambition here is punished quickly. The environment does not tolerate improvisation. It enforces precision, and even precision is sometimes not enough. Scientists understand this intellectually long before a mission begins. They have seen the failure reports. They have studied past losses. They know how many systems must function perfectly, simultaneously, for a single dive to succeed. That knowledge does not fade during operations, it sharpens. Every descent reinforces the awareness that success depends on a chain of conditions, any one of which can break. Unlike surface fieldwork, trench exploration offers no gradual adjustment period. On land, environments become familiar through repeated exposure. Researchers learn how weather behaves, how terrain responds, how equipment performs. In trenches, repetition is rare. Each expedition may be separated by years. Personnel change, technology evolves, institutional memory fragments, familiarity never fully develops. This lack of routine contributes to discomfort. The trench never becomes ordinary. It never becomes a background setting. Each return feels provisional, as though the environment must be relearned every time. Small anomalies that might be dismissed elsewhere receive intense scrutiny, because the cost of ignoring them is too high. There is also the persistent awareness of invisibility. Most of what happens during a trench dive cannot be seen directly. Operators rely on telemetry, sensor readouts, and narrow video feeds. They do not see the vehicle itself, only what its instruments report. When something goes wrong, diagnosis is indirect. A pressure reading shifts, a motor draws unexpected current, a signal drops. The cause remains hidden behind kilometers of water. This separation between action and consequence creates psychological strain. Decisions must be made based on incomplete information, under time pressure, with limited ability to intervene. Abort too early and the mission fails without data. Wait too long and recovery may be impossible. The correct choice is rarely obvious. The environment itself reinforces this tension. The trench does not provide stable reference points. The seafloor is uneven, slopes shift, sediments move. What was safe terrain during one descent may not be during the next. Maps become outdated quickly. Confidence in prior knowledge erodes. Even biological encounters contribute to unease. Life exists in the trench, but it does so quietly and sparsely. Organisms appear briefly, often alone, then vanish. There are no large-scale patterns visible in real time, no clear sense of ecosystem structure. This absence of visual continuity makes the environment feel less predictable, less readable. Scientists are trained to look for patterns. Trenches frustrate this impulse. Data arrives in fragments, each requiring careful contextualization. Statistical confidence is harder to establish. Variability is difficult to separate from noise. Conclusions are tentative by necessity, which can feel unsettling in a field that values robustness. There is also the issue of irreversibility. Mistakes at the surface can often be corrected. Instruments can be repaired. Sites can be revisited. In trenches, errors are final. A lost vehicle is lost permanently. A missed opportunity may not return for decades. This asymmetry heightens the emotional stakes of every decision. Even when missions succeed, unease does not vanish. Data interpretation introduces its own uncertainties. Measurements taken under extreme conditions may not translate cleanly to surface-based models. Pressure effects on sensors are not always fully understood. Calibration drift may go unnoticed. Scientists must question their own results, aware that the environment itself may have altered the instruments in subtle ways. There is also the broader awareness that trench processes operate on scales beyond human control. Earthquakes can occur at any time. Landslides can reshape terrain between deployments. Volcanic activity can alter chemical conditions without warning. These events do not announce themselves in advance, they simply happen. This unpredictability contrasts sharply with the controlled environments many scientists are accustomed to. Laboratories offer repeatability. Variables can be isolated. Trenches offer none of this. They are open systems influenced by forces that cannot be paused or adjusted. Distance amplifies the feeling. The trench lies far from populated areas, far from immediate assistance, far from infrastructure. Expeditions operate at the edge of logistical feasibility. Weather windows are narrow. Supply chains are long. If something fails, replacement may be impossible until the next field season, if there is one. Human vulnerability, while indirect, is never absent. Even unmanned missions involve crews working long hours in challenging conditions. Fatigue accumulates. Decisions must be made despite exhaustion. The awareness that rescue options are limited extends beyond the vehicle to the people supporting it. There is also a philosophical dimension to the unease. Trenches challenge the assumption that knowledge leads to comfort. In many domains, understanding reduces fear. In trenches, understanding often sharpens it. Knowing how pressure behaves does not make it less dangerous. Knowing how subduction works does not make earthquakes less disruptive. Knowledge reveals scale rather than control. Scientists working in these environments develop a different relationship with uncertainty. It is not something to be eliminated, but something to be managed. Models are built with explicit acknowledgement of what they cannot capture. Results are framed cautiously. Confidence intervals widen. This cautious mindset can feel at odds with public expectations. Popular narratives often portray exploration as heroic and decisive. Trenches resist this framing. Progress is slow, discoveries are incremental, setbacks are common. Unease is part of the process, not a sign of weakness. There's also the sense that the trench does not respond to observation. It does not reveal itself more willingly with increased attention. It does not become more predictable over time. Each descent offers information, but the environment remains fundamentally indifferent. This indifference is perhaps the most unsettling aspect. On land, environments often show signs of human presence. Trails form, equipment leaves marks, trenches erase intrusion quickly, sediments settle, darkness returns, the environment resets as though the visit never occurred. Scientists are acutely aware of this asymmetry. Their presence is temporary. The trench's existence is effectively permanent on human timescales. This imbalance fosters humility, but also a quiet discomfort. It is difficult to feel at ease in a place that does not acknowledge you. The unease is reinforced by scale mismatches. Human senses evolved for environments measured in meters and minutes. Trenches operate in kilometers and geological time. Instruments extend reach, but they do not change perspective entirely. Data must be translated, abstracted, and interpreted through layers of mediation. This translation process introduces distance between observation and understanding. Scientists work with representations rather than direct experience. They analyze graphs rather than landscapes. They infer processes rather than witnessing them. The gap between reality and representation never fully closes. There is also the awareness that many questions may remain unanswered indefinitely. Some processes occur too slowly. Some environments are too inaccessible. Some variables cannot be isolated. This acceptance runs counter to the scientific drive to resolve uncertainty. Yet this acceptance is also what allows work to continue. Scientists learn to operate without closure, to value partial understanding, to recognize that unease does not invalidate inquiry. It contextualizes it. Over time, this persistent unease becomes familiar. It does not disappear, but it becomes part of the background, like the pressure itself. Scientists adjust expectations. They design experiments that acknowledge limits. They build redundancy where possible and accept loss where necessary. Still, even seasoned researchers report a subtle shift when dealing with trenches, a heightened attention to detail, a slower decision-making pace, a reluctance to assume stability. These are not emotional reactions in the traditional sense. They are adaptive responses to an environment that punishes complacency. The trench teaches that some places cannot be made comfortable through knowledge alone. They require respect, caution, and restraint. Unease becomes a form of awareness, a signal that the environment operates beyond familiar bounds. This awareness does not deter exploration. It shapes it. It ensures that curiosity is tempered by humility, that ambition is balanced by caution, and that understanding is pursued without the illusion of mastery. As attention shifts toward what may still lie hidden within the trench, this unease remains present, not as a warning to retreat, but as a reminder to proceed carefully. The trench does not invite confidence. It demands attentiveness. In that sense, the unease scientists feel is not a flaw in the process. It is evidence that the process is aligned with reality. It reflects an understanding that some environments do not become safer simply because they are studied. The Kermadec Trench remains one of those places, known, measured, and modelled, yet never fully familiar. Each descent reinforces the same lesson. Knowledge can illuminate, but it does not domesticate. And in the deepest parts of the ocean, that distinction matters. Even after decades of mapping, sampling, modelling, and cautious descent, the Kermadec Trench remains defined as much by absence as by knowledge. scientists can outline its shape, estimate its depth, describe its tectonic role, and list the organisms that have been observed there. Yet beneath all of that sits a persistent understanding that what has been seen represents only a fraction of what exists, not because the trench is deliberately secretive, but because its conditions make complete observation extraordinarily difficult. One of the most significant unknowns involves biological diversity. Every expedition adds new genetic sequences to databases, many of which do not match anything previously recorded. These fragments suggest organisms that have never been directly observed, species known only through molecular traces recovered from sediments or water samples. Each sequence implies a lineage adapted to extreme conditions, potentially carrying biochemical strategies that differ in subtle but important ways from those already studied. These unknown organisms may not be large or visually striking. In fact, they are more likely to be microbial, operating at scales that rarely register in video footage. Yet microbial life plays a disproportionate role in ecosystem function. It drives nutrient cycling, mediates chemical reactions, and forms the base upon which more complex organisms depend. Changes or variations at this level can reshape entire systems. There is also the possibility that Hadal ecosystems function differently from current models suggest. Most ecological frameworks are built around relatively stable energy inputs and predictable interactions. Trenches violate these assumptions. Energy arrives irregularly. Disturbance is common. Pressure alters reaction rates. Darkness removes visual signaling entirely. These conditions may produce ecological dynamics that do not resemble surface or even abyssal systems. Some researchers suspect that trench ecosystems may rely more heavily on episodic events than previously thought. Large food falls, sediment slumps, or chemical releases associated with tectonic activity could act as ecological reset points, restructuring communities repeatedly. If so, the trench would not be a static environment populated by stable populations, but a system defined by cycles of disruption and recovery that operate over long timescales. Chemical processes also remain poorly understood. The interaction between subducting plates, sediments, and seawater creates unique geochemical environments. Fluids released from descending crust may migrate upward through faults, altering the chemistry of surrounding sediments and water. These fluids can carry dissolved metals, gases, and other compounds that influence microbial metabolism. Some of these reactions occur at pressures and temperatures that are difficult to reproduce in laboratories. As a result, scientists rely on indirect indicators to infer what might be happening. This leaves room for processes that have not yet been recognized or fully described. Entire metabolic pathways may exist that operate only under Hadal conditions. There is also the question of physical structure. High-resolution mapping of the trench floor remains incomplete. Steep walls, overhangs, and fractured rock formations may host microhabitats that have never been sampled. Small variations in terrain can create localized conditions that support specialized communities. Without comprehensive coverage, these pockets remain invisible. Sediment layers themselves hold records of past events. Each layer represents a moment in geological time, capturing information about earthquakes, landslides, and changes in ocean productivity. Interpreting these records requires careful sampling and dating, yet many sections of the trench have never been cored. The history they contain remains locked beneath kilometers of water and pressure. Some scientists are particularly interested in the potential for unknown seismic behaviors. Subduction zones are complex systems, and not all of their behaviors are well understood. Slow-slip events, where plates move gradually without producing traditional earthquakes, have been documented in some regions, but remain poorly characterized in deep trench environments. These events could influence stress accumulation and release in ways that affect seismic hazard assessments. The trench may also conceal links between deep geological processes and surface phenomena that have yet to be identified. Changes occurring deep within the subducting slab could influence volcanic activity, ocean chemistry, or even long-term climate patterns. Tracing these connections requires integrated data sets that span disciplines and timescales, something that remains challenging given current observational limits. Another area of uncertainty involves adaptation limits. While life has been documented at extreme depths, it is not clear how close these organisms operate to their physiological thresholds. Small changes in pressure, temperature, or chemistry could push them beyond viability. Understanding these limits matters not only for ecology, but for predicting how trench systems might respond to environmental change. Human influence adds further complexity. Pollutants have already reached Hadal depths, but their long-term effects remain unknown. Some compounds may accumulate slowly, altering biological processes over generations. Others may interact with extreme conditions in unexpected ways, producing byproducts that do not form elsewhere. The trench could be hosting chemical experiments driven unintentionally by surface activity. There is also the possibility that the trench contains materials of scientific value that have not yet been recognized. Unique mineral formations, unusual isotopic signatures, or novel compounds produced under extreme pressure could offer insights into planetary processes or even technological applications. Without targeted exploration, these remain hypothetical. Technological limitations ensure that much of this remains speculative. Instruments capable of long-term deployment at Hadal depths are rare. Power supply, data storage, and retrieval all impose constraints. Autonomous systems must balance endurance with functionality. Every design choice involves trade-offs that limit what can be observed. Even when data is collected, interpretation remains cautious. Measurements taken under extreme conditions may not behave as expected. Sensors calibrated at the surface may drift. Materials may respond differently under pressure. Separating genuine signals from artifacts requires careful analysis, and often leaves room for alternative explanations. This uncertainty does not indicate failure. It reflects the nature of the environment. The trench operates at the intersection of multiple extremes, each amplifying the others. Observation is possible, but never comprehensive. Understanding advances, but never reaches closure. The Kermadec Trench exemplifies this tension between knowledge and mystery. It is one of the most studied deep ocean trenches, yet it continues to produce findings that challenge expectations. Each expedition answers some questions and raises others, expanding the boundary of what is known while preserving a core of uncertainty. There is also the matter of scale. Processes occurring in the trench unfold over timescales that far exceed typical research projects. Some changes may take centuries to manifest. Others may be triggered by rare events separated by thousands of years. Human observation windows are narrow by comparison, capturing moments rather than narratives. This temporal mismatch ensures that some aspects of the trench will remain hidden, simply because they do not align with human timeframes. Detecting slow trends requires long-term monitoring that may not be feasible. Understanding rare events requires patience that extends beyond individual careers. Despite these challenges, curiosity persists. Scientists continue to design new instruments, refine models, and propose experiments that push deeper and last longer. Each technological advance expands the observational envelope slightly, revealing new details while reinforcing how much remains beyond reach. The trench also serves as a reminder that exploration does not always lead to domestication. Some environments remain fundamentally resistant to familiarity. They allow glimpses, not immersion. They reward caution rather than boldness. What the trench might still be hiding is therefore not a single discovery, but a collection of processes, organisms, and interactions that operate quietly under conditions that resist direct study. It may be hiding alternative strategies for life, unfamiliar chemical cycles, or subtle geological behaviours that influence the planet in ways not yet fully appreciated. This hiddenness is not accidental. It is a consequence of scale, pressure, and distance. The trench does not conceal by design. It simply exists under conditions that make concealment inevitable. As attention turns toward the final descent in this long exploration, the sense of incompleteness remains, not as frustration, but as context. The trench is not a puzzle waiting to be solved entirely. It is a system to be approached gradually, respectfully, and with the understanding that some aspects may always remain beyond reach. In that sense, what the Kermadec Trench might still be hiding is not just information, but perspective. It reminds scientists that knowledge grows outward from uncertainty, not toward its elimination. That understanding deepens not by closing questions, but by refining them. And as the focus begins to rise slowly back toward the surface, away from pressure and darkness, the awareness lingers that beneath the calm ocean lies a place that continues to operate largely on its own terms. A place that offers insight without surrender and mystery without spectacle. Coming back to the surface is not a physical ascent so much as a gradual reorientation. There is no sudden transition where the deep ocean releases its hold and familiarity snaps back into place. Instead, perspective shifts quietly, layer by layer, much like the descent itself. Pressure lessens. Darkness gives way to dim blue light. Temperature rises almost imperceptibly. The environment becomes more forgiving, but the understanding carried upward does not fade as easily. After spending time thinking about the trench, it becomes difficult to look at the ocean surface the same way again. What once appeared calm and uniform now feels thin, like a skin stretched over immense depth and activity. The waves no longer suggest openness alone. They hint at what lies beneath, not in a threatening sense, but in a grounding one. The ocean becomes heavier, more substantial, shaped by processes that extend far beyond what the eye can see. The Kermadec Trench does not announce itself at the surface. There are no visible markers, no signs that such depth and pressure exist below. Ships pass overhead unaware. Weather systems form and dissipate without reference to what lies beneath them. This disconnect is part of what makes the trench so affecting. Its influence is vast, yet its presence is almost entirely concealed. Returning attention upward also brings a renewed awareness of scale. Human concerns operate in minutes, hours, and years. The trench operates in kilometers and millions of years. Earthquakes release energy built up over centuries. Plates move steadily without regard for observation. Ecosystems adapt over timescales that outlast institutions and careers. Holding these scales together in the mind changes how importance is assigned. Problems that once felt immediate can feel smaller by comparison, not because they lack significance, but because they occupy a narrower slice of reality. At the same time, responsibility feels larger. Knowing that surface activity leaves traces even in the deepest trenches reframes ideas about isolation and consequence. There is no true separation between above and below. Material, energy, and influence circulate continuously. Coming back to the surface also reframes what exploration means. It is tempting to think of exploration as a process of conquest or completion, where unknowns are converted into knowledge and then set aside. The trench resists this narrative. It suggests a different model, one where exploration is an ongoing relationship rather than a finite task. In this model, understanding does not eliminate mystery. It coexists with it. Each new insight clarifies one aspect while revealing others that remain unresolved. The trench does not become familiar through repeated study. It becomes better contextualized, better respected, but never fully known. This has implications beyond oceanography. It challenges the assumption that all systems can be mastered given enough data and time. Some systems are too large, too deep, or too complex to be reduced to complete certainty. Accepting this does not weaken science. It strengthens it by aligning expectations with reality. The experience of studying trenches shapes scientists in subtle ways. It encourages patience, it rewards caution, it fosters collaboration across disciplines that might otherwise remain separate. Geology, biology, chemistry, physics and engineering intersect here out of necessity rather than convenience. It also alters how success is defined. In trench research, success may be a single intact dataset, a brief observation of a species, or confirmation that a model holds under extreme conditions. These outcomes may seem modest from the outside, but they carry weight because of the effort required to achieve them. Returning to the surface also restores sensory richness. Light behaves normally again, sound travels predictably, temperature varies with weather and time of day. These familiar cues reassert themselves, but they do so against the backdrop of what has been considered. The surface feels less like the default state and more like one layer among many. There is a quiet shift in how fragility is perceived. At depth, life persists under conditions that destroy machines. At the surface, life appears abundant but is often far more vulnerable to change. This inversion challenges assumptions about resilience and highlights how adaptation depends on context. The trench does not offer comfort, but it offers clarity. It reveals that the planet operates through processes that do not prioritize human convenience. Stability, where it exists, is temporary. Change is constant, even when it unfolds slowly. This clarity can be unsettling, but it can also be grounding. It places human activity within a broader framework, one that emphasizes continuity over immediacy. The trench reminds observers that the Earth has a long history of change and will continue to evolve regardless of observation. Coming back to the surface also brings attention to responsibility. The realization that pollutants and debris reach even the deepest parts of the ocean underscores how interconnected systems are. Actions taken far from the trench influence it indirectly. There are no true margins where impact disappears. This awareness does not demand alarm. It encourages thoughtfulness. It suggests that stewardship must account for systems that operate beyond visibility. Protection cannot rely solely on what is seen or valued culturally. It must extend to environments that resist familiarity. The trench also alters how uncertainty is viewed. Instead of being treated as a problem to be solved, uncertainty becomes a feature to be navigated. It guides research questions, shapes experimental design, and tempers conclusions. This approach does not slow progress, it directs it more honestly. As attention returns fully to the surface world, the trench remains present in memory not as an image, but as a framework. It influences how depth, time, and scale are understood. It lingers as a reference point against which other environments are measured. The surface ocean becomes more complex as a result. It is no longer just a boundary between air and water. It is the uppermost layer of a vast vertical system. Weather, climate, and biology are connected downward through layers that extend far beyond reach. Even land takes on a different quality. Continents feel less permanent, knowing they are carried by plates that move slowly but persistently. Mountains are recognized as temporary features. Stability becomes relative rather than absolute. This shift does not diminish the value of the surface world. It deepens it. Familiar environments gain meaning through their connection to deeper systems. What appears static is understood as momentarily balanced. The process of coming back to the surface is therefore not about leaving the trench behind. It is about integrating its lessons. The trench does not need to be revisited physically to remain influential. Its existence alone reshapes perspective. And so, as the descent ends and attention settles back into the rhythms of the surface, there is no sense of conclusion in the traditional sense. Nothing has been resolved completely. No final answers have been delivered. That is appropriate. The trench does not offer endings. It offers context. If there is a change, it is internal rather than external, a recalibration of scale. a quiet adjustment in how certainty is held, a recognition that some of the most important systems on the planet operate far from view, shaping conditions silently and continuously. And if this long descent and careful return offered any calm, or perhaps a different way of thinking about depth, distance, and patience, then that quiet shift is enough. Curiosity does not need to rush. Understanding does not need to be complete. For now, the surface is where attention rests again. Light returns, sound softens, breathing feels easier. But beneath it all, the trench remains, doing what it has always done, shaping the planet without asking to be noticed. And somewhere between what is known and what remains out of reach, between pressure and release, between descent and return, there is space for wonder to settle, unhurried, as the ocean continues its work below.